The question of what caused the Big Bang is one of the most profound mysteries in science. The Big Bang theory describes the universe's expansion from an extremely hot, dense state about 13.8 billion years ago. It explains much of what we observe today, such as the cosmic microwave background radiation and the ongoing expansion of galaxies. However, the question of what set it all in motion, what caused the Big Bang, remains unanswered. To understand the problem, it helps to start with what we do know. The Big Bang theory doesn't describe the very beginning of everything. Instead, it starts just after time zero, a fraction of a second after whatever event initiated the universe. At this point, the universe was unimaginably small and hot. Space, time, and matter were all compressed into a singularity, a point of infinite density. From there, the universe began to expand, cooling as it grew. Over time, energy transformed into particles, atoms formed, and eventually stars and galaxies emerged. Physicists often describe this initial expansion in terms of mathematics and physics. For example, Einstein's general theory of relativity helps us understand how space and time behave under extreme conditions. According to the theory, space and time themselves came into existence with the Big Bang. This means that asking what came before the Big Bang might not even make sense in the way we usually think about cause and effect. Time as we know it began with the Big Bang, so before might not be a meaningful concept. That said, scientists still explore possibilities for what could have triggered the Big Bang. Some theories propose that the Big Bang was not the true beginning, but part of a larger cycle. One idea suggests the universe goes through endless cycles of expansion and contraction. In this scenario, a previous universe might have collapsed in a big crunch, and the energy from that collapse triggered the expansion we call the Big Bang. This cyclic model solves the problem of a singular beginning by suggesting there is always something before. However, this theory raises its own questions, like what started the first cycle. Another idea comes from quantum mechanics, which deals with the behavior of particles at extremely small scales. Quantum mechanics introduces uncertainty and randomness into the fabric of reality. Some physicists propose that quantum fluctuations, tiny random changes in energy, in a pre-existing quantum field could have sparked the Big Bang. These fluctuations could create a region of space where energy became dense enough to trigger the rapid expansion. If this is true, the universe might have emerged from something rather than nothing. However, this idea depends on assumptions about what existed before our universe and how quantum mechanics operated in such conditions. One of the most fascinating proposals involves the concept of a multiverse. In this view, our universe is just one of countless others. Imagine bubbles in a vast cosmic foam. Each bubble represents a universe, and new bubbles form constantly. The Big Bang, in this scenario, is simply the formation of our bubble. This idea comes from certain interpretations of string theory and inflation, a process that describes how the early universe expanded incredibly quickly. If the multiverse idea is correct, then what caused the Big Bang might be a process happening all the time across an infinite number of universes. However, testing this theory is incredibly difficult since we can't currently observe other universes. Another approach involves understanding the role of gravity and space-time. Some scientists suggest that our universe might have emerged from a black hole in another universe. In this model, the singularity inside a black hole could create a new region of space-time, which might expand to form a new universe. This idea connects the Big Bang to the extreme physics of black holes, which are also regions of infinite density. It's an intriguing thought, but again, the evidence to support it is limited. Religious and philosophical perspectives also address this question. Many people wonder whether the Big Bang was the result of a divine act or some purposeful creation. These interpretations are outside the realm of science, which relies on testable and observable evidence. However, they highlight the human need to understand our origins and the larger meaning of existence. The search for answers about the Big Bang continues with cutting-edge experiments and observations. Scientists use powerful telescopes to study the earliest light in the universe, known as the cosmic microwave background. This light provides clues about the conditions just after the Big Bang. Particle physicists use giant machines like the Large Hadron Collider to recreate high-energy conditions similar to those in the early universe. These experiments help us understand the fundamental forces and particles that shaped everything we see today. Despite these efforts, the ultimate cause of the Big Bang remains elusive. One challenge is that as we look closer to the moment of the Big Bang, the laws of physics as we know them begin to break down. For example, the singularity at the beginning of the universe involves infinite density, a condition where our current theories of gravity and quantum mechanics no longer work together. To solve this, scientists are searching for a theory of quantum gravity, which would unite these two frameworks. Such a theory might offer new insights into what caused the Big Bang. Another obstacle is the lack of direct evidence about the very beginning. Observations can only take us back so far. The light we see from the earliest moments of the universe comes from about 380,000 years after the Big Bang. Before that, the universe was opaque, and we can't observe it directly. This cosmic curtain makes it hard to test ideas about what happened at the very start. Although we may not have definitive answers yet, the pursuit of this question drives scientific progress. Each new discovery about the universe's origins brings us closer to understanding not just where we come from, but also the nature of reality itself. The question of what caused the Big Bang may turn out to be unanswerable in the way we hope, or it might require a completely new way of thinking about time, space, and existence. The mystery of the Big Bang reminds us of the vast unknowns in the universe. It challenges us to keep exploring, questioning, and expanding our understanding. The search itself is valuable, offering insights not only into the cosmos, but also into the limits and possibilities of human knowledge. Whether we ever find a complete answer or not, the quest to understand what caused the Big Bang will continue to inspire curiosity and wonder for generations to come. Dark matter and dark energy are two of the most mysterious concepts in modern science. Together, they make up about 95% of the universe, yet we cannot directly see or measure them with our current tools. Scientists came up with these ideas because they noticed things in the universe that didn't make sense if only visible matter and energy were at play. Understanding these unseen components is crucial to understanding how the universe works. Let's start with dark matter. Imagine you're looking at a spiral galaxy through a telescope. The galaxy spins, and you might expect that the stars near the center would move faster than those near the edges, just like how planets in our solar system move faster when they are closer to the sun. But scientists observed something strange. Stars at the edges of galaxies move just as fast as those near the center. This doesn't fit with what we know about gravity. According to our understanding, the visible matter in the galaxy doesn't have enough mass to hold the galaxy together at those speeds. If only the visible stars and gas were there, galaxies should fly apart. To explain this, scientists proposed that there must be something else present, something we can't see but that has mass and exerts gravitational pull. They called it dark matter. It's dark because it doesn't emit, absorb, or reflect light, making it invisible to telescopes. We only know it's there because of the effect it has on visible objects. Imagine walking through a dark room. You might not see a table, but if you bump into it or notice how other objects behave around it, you know it's there. Dark matter works in a similar way. We can't see it directly, but we see its effects on the movement of stars and galaxies. Scientists have tried to figure out what dark matter is made of. Some think it might consist of particles we haven't discovered yet. These hypothetical particles have names like WIMPs, which stands for Weakly Interacting Massive Particles. The name suggests that these particles interact very little with normal matter, except through gravity. Others suggest axions, another type of theoretical particle, might make up dark matter. Despite many experiments, no one has directly detected these particles yet. So dark matter remains one of the biggest mysteries in science. Now, let's move on to dark energy. While dark matter helps explain how galaxies hold together, dark energy helps explain something even bigger: why the universe is expanding faster and faster. For a long time, scientists thought the expansion of the universe might slow down over time because of gravity. After all, if you throw a ball into the air, gravity pulls it back down. Similarly, the gravity from all the matter in the universe should slow the expansion. But when scientists measured how fast the universe was expanding, they found the opposite. The expansion isn't slowing down, it's speeding up. This unexpected result was first discovered in the late 1990s by teams studying distant supernovae. These exploding stars are like cosmic mile markers, helping scientists measure distances in the universe. What they found shocked everyone. Something must be pushing the universe outward, counteracting gravity. They called this mysterious force dark energy. Dark energy is even harder to study than dark matter because it doesn't clump together or interact with matter in any obvious way. Instead, it seems to work uniformly across space, affecting the entire universe at once. One way to think about it is to imagine a balloon. As you blow air into the balloon, it expands. Dark energy acts like the air, but instead of a single balloon, it's expanding the fabric of space itself. There are a few ideas about what dark energy might be. One possibility is that it's related to what scientists call the cosmological constant. This idea goes back to Albert Einstein, who added it to his equations when he thought the universe was static, not expanding or contracting. Later, he called it his biggest blunder when it was discovered the universe was expanding after all. But now the cosmological constant has made a comeback, as it might explain the accelerating expansion of the universe. It represents a kind of energy that is built into the very fabric of space. As the universe grows, this energy doesn't dilute. It stays constant, continuing to push the expansion. Another idea is that dark energy might come from something dynamic, not constant, like a field that changes over time. Scientists sometimes call this a quintessence field, borrowing a term from ancient philosophy. Unlike the cosmological constant, this type of energy could vary in strength or act differently in different parts of the universe. The challenge with both dark matter and dark energy is that they don't fit neatly into the standard model of physics, which describes the known particles and forces in the universe. This means scientists need to think beyond what we currently know. They use tools like powerful telescopes, particle accelerators, and computer simulations to gather more clues. For example, telescopes like the Hubble Space Telescope help scientists map the distribution of galaxies and see how they move. These observations provide indirect evidence of dark matter and dark energy. Despite the progress, these mysteries raise more questions than answers. If dark matter and dark energy exist, why can't we detect them directly? Are they made of something entirely new, or do they reflect gaps in our understanding of gravity or other fundamental forces? Some scientists even wonder if these concepts are placeholders for something we don't yet understand about the universe itself. To put it into perspective, imagine you're trying to solve a puzzle, but you only have 5% of the pieces. That's the part of the universe we can see and understand. The other 95, dark matter and dark energy, are the missing pieces. Without them, the picture doesn't make sense. Galaxies wouldn't hold together, and the universe wouldn't expand the way it does. While this might sound frustrating, it's also exciting. These mysteries push scientists to explore new ideas and develop new tools. Every small discovery adds to our understanding, even if it doesn't provide all the answers. For example, scientists have ruled out certain types of particles as candidates for dark matter, narrowing the possibilities. They've also measured the expansion of the universe with incredible precision, providing more clues about dark energy. Dark matter and dark energy remind us that there's still so much we don't know about the universe. They challenge our understanding of physics and encourage us to think in new ways. The search for answers continues, with scientists around the world working to uncover the secrets of these unseen forces. Though the answers remain out of reach for now, each step forward brings us closer to understanding the universe's most profound mysteries. Physicists think there must have been a small imbalance between matter and antimatter in the early universe, with slightly more matter particles than antimatter particles. This imbalance would mean that, after most of the matter and antimatter annihilated each other, a small amount of matter would remain. This leftover matter became the building blocks of everything we see in the universe today. The big mystery is figuring out why this imbalance occurred in the first place. One idea involves a property of particles called charge parity, or CP symmetry. CP symmetry is a way of saying that the laws of physics should apply equally to particles and their antiparticles. If CP symmetry were perfect, then matter and antimatter would behave in identical ways, and there would be no reason for one to dominate over the other. However, experiments have shown that CP symmetry is not perfect. In certain cases, particles and antiparticles behave slightly differently. This tiny difference, called CP violation, could be the key to understanding why there is more matter than antimatter. To see CP violation in action, scientists study particles like kaons and B-mesons. These are unstable particles that exist only briefly before they decay into other particles. By closely observing these decays in laboratory experiments, physicists have detected small but measurable differences in how kaons and B-mesons decay compared to their antiparticles. These differences provide concrete evidence that nature does not treat matter and antimatter exactly the same. However, the CP violation observed so far is not large enough to fully explain the imbalance between matter and antimatter in the universe. It's a clue, but it's not the whole story. Another idea is that the imbalance might have been created during a process called baryogenesis. This is a theoretical mechanism that could have occurred in the early universe, just fractions of a second after the Big Bang. During baryogenesis, interactions between fundamental particles could have produced more baryons, a category of particles that includes protons and neutrons, than antibaryons. For baryogenesis to work, three conditions, known as the Sakharov conditions, must be met. First, there must be processes that violate the conservation of baryon number, which is the rule that baryons and antibaryons are always created in equal numbers. Second, CP symmetry must be violated, allowing matter and antimatter to behave differently. Third, the universe must be out of thermal equilibrium, meaning that it must cool in a way that favors the creation of matter over antimatter. These conditions provide a framework for understanding how matter could have come to dominate the universe, but the exact details remain elusive. Scientists have proposed various theories about how baryogenesis might have worked. Some involve exotic particles that existed only in the extreme conditions of the early universe, while others rely on the behavior of known particles under high-energy conditions. The challenge is that these ideas are hard to test. The conditions of the early universe cannot be easily recreated, even in the most advanced particle accelerators. The search for answers continues through both experiments and observations. Particle accelerators like the Large Hadron Collider allow scientists to probe the properties of particles and look for new forms of CP violation. At the same time, astrophysical observations provide clues about the early universe. For example, studying the cosmic microwave background, the faint glow left over from the Big Bang, can reveal details about the distribution of matter and antimatter in the universe's infancy. Some researchers have also explored the possibility that antimatter might still exist in isolated regions of the universe. If large amounts of antimatter survived in distant galaxies, it would offer a different explanation for the observed imbalance. However, no evidence of such antimatter galaxies has been found. When matter and antimatter collide, they produce gamma rays, a specific form of high-energy light. Scientists have searched the cosmos for signs of these gamma rays and found none, suggesting that antimatter is not present in significant amounts. The mystery of why there is more matter than antimatter touches on some of the deepest questions about the nature of reality. It forces us to confront the fundamental laws of physics and ask whether they are complete or if there are aspects we have yet to uncover. It also reminds us of how fragile and unique our existence is. If the imbalance between matter and antimatter had been slightly different, the universe might have been a vastly different place, or it might not have existed at all. While we do not yet have a complete answer, the pursuit of this mystery drives progress in many areas of science. It challenges our understanding of the universe's origins and pushes the boundaries of what we can explore in the lab and through observations of the cosmos. The more we learn, the closer we come to uncovering the truth about why the universe is filled with matter and why we are here to wonder about it. Time is something we all experience, yet it remains one of the most mysterious aspects of our universe. We use time to organize our lives, track changes, and measure motion. But what exactly is it? Scientists, philosophers, and thinkers have debated the nature of time for centuries. Some view it as a fundamental part of the universe, while others suggest it might only be a product of our perception. To understand time better, we need to explore how it behaves and why it feels so familiar but so puzzling at the same time. We often think of time as a straight line that moves from the past through the present and into the future. This idea fits with our everyday experience. The clock ticks forward, we age, and events unfold one after another. This simple view of time has worked well for most of human history, but modern science shows it might not tell the whole story. For example, Einstein's theory of relativity introduced a new way to think about time. According to relativity, time is not separate from space. Instead, the two combine to form what we call space-time. This means time isn't universal. It can stretch or shrink depending on the situation. Imagine you are standing still, holding a clock, and your friend is moving quickly in a spaceship with another clock. When the two of you compare your clocks, you'll find they show different times. This effect, called time dilation, has been tested with experiments and confirmed to be true. It happens because the faster you move, the slower time passes for you compared to someone who is standing still. This phenomenon is strange because it shows time is not fixed. It changes depending on speed and gravity. Gravity also affects time in surprising ways. The stronger the gravitational field, the slower time moves. Scientists have measured this effect near large objects like planets or stars. Even on Earth, time runs slightly faster at the top of a mountain than it does at sea level because the pull of gravity is weaker higher up. These discoveries reveal that time is flexible, not the rigid, unchanging thing we once believed. Some scientists go even further and suggest time might not be as fundamental as we think. They propose that time could be an emergent property, something that arises from deeper, underlying processes. To understand this, think about how temperature works. Temperature doesn't exist on its own. It's the result of countless molecules moving and interacting. In a similar way, time might emerge from the way particles and forces interact at a microscopic level. This idea is still theoretical, but it offers a new way to think about what time really is. Another perspective comes from quantum mechanics, which deals with the smallest particles in the universe. At this tiny scale, the usual rules of time seem to break down. In the everyday world, events happen in order. A cause leads to an effect. But in the quantum world, events can seem random, and particles can exist in multiple states at once. Some researchers wonder if time as we know it even exists at this level. If it doesn't, time might only appear real because of the way we perceive it in the larger macroscopic world. Our perception of time adds another layer to the mystery. Humans experience time in a linear way, moving from one moment to the next. But this might be a result of how our brains work rather than a feature of the universe itself. Studies suggest that our sense of time depends on memory and anticipation. We remember the past and imagine the future, creating the feeling of time flowing forward. Without this mental framework, our experience of time could be very different. Some cultures and languages also view time differently. In English, we talk about the past as being behind us and the future as ahead. But some cultures describe time as moving vertically, with the past below and the future above. These differences show that how we think about time is shaped by more than just physics. It's also influenced by culture and language. The question of whether time has a beginning or an end is another area of debate. Many people think about time as infinite, stretching forever in both directions. But the Big Bang Theory suggests the universe had a starting point about 13.8 billion years ago. This raises a big question. Did time begin with the Big Bang? If so, what happened before that? Some scientists argue that it doesn't make sense to ask what came before time started, just as it doesn't make sense to ask what's north of the North Pole. Others suggest that time might be cyclical, with no true beginning or end, like a loop that repeats itself. One of the strangest ideas about time comes from the concept of block time. This view suggests that the past, present, and future all exist at once, like a single, unchanging block. In this model, time doesn't flow the way we experience it. Instead, all moments are equally real, and our sense of moving through time is an illusion. This idea challenges everything we take for granted about time and raises deep philosophical questions. For example, if all moments exist at once, does that mean the future is already determined? If so, what happens to free will? These questions don't have clear answers, but they show how closely the nature of time is tied to our understanding of reality and ourselves. Time also plays a crucial role in the second law of thermodynamics, which says that entropy, or disorder, tends to increase over time. This law gives time its arrow, pointing from the ordered past to the more disordered future. Without this arrow, time might feel directionless, like space. But some scientists wonder if the arrow of time is just a byproduct of how we observe the universe, rather than a fundamental property of time itself. When we think about time, we often focus on its physical and scientific aspects, but time also has a deeply personal and emotional dimension. We measure our lives in seconds, minutes, and years, but we experience time differently depending on the situation. A happy moment might feel like it flies by, while a painful experience can feel endless. This subjective nature of time makes it hard to define in purely objective terms. The true nature of time might never be fully understood. It could be a fundamental part of the universe, an emergent property, or even an illusion created by our perception. Each of these possibilities challenges us to rethink our place in the universe and how we experience reality. What's clear is that time is more than just the ticking of a clock or the changing of the seasons. It's a profound mystery that touches every aspect of our lives, from the physical to the philosophical. In the end, time might not have a single simple explanation. It could be many things at once, depending on how you look at it. This complexity makes time one of the most fascinating and puzzling aspects of our universe. Whether we're measuring the orbits of planets, studying the behavior of particles, or reflecting on our own experiences, time remains a central part of the human experience, and its mysteries continue to inspire wonder and curiosity. Many people wonder if our world is limited to the three dimensions we experience daily. These dimensions, length, width, and height, are so ingrained in how we think and move that it's hard to imagine anything beyond them. But scientists have long asked whether there might be more dimensions that we can't see. The idea is not just the stuff of science fiction. It has deep roots in physics and mathematics, and it might help us solve some of the biggest mysteries in science. To understand extra dimensions, it helps to think about what we mean by a dimension. A dimension is a direction in which you can move. Imagine a straight line. You can only go forward or backward, so the line is one-dimensional. Now imagine a flat sheet of paper. You can move forward, backward, left, or right, which makes the paper two-dimensional. In the three-dimensional space we live in, you can also move up and down. Each new dimension adds a way to move that didn't exist before. Now imagine you are a two-dimensional creature living on a flat sheet of paper. You can't move up or down, so you can't see anything outside your flat world. If someone were to lift an object off the paper and hold it above you, the object would disappear from your view. You might not even know the third dimension exists. This is how some scientists explain the idea of extra dimensions. Just as a flat creature can't see up and down, we might not be able to see dimensions beyond our three. Why would anyone think extra dimensions exist? One reason comes from physics. Scientists have been trying to understand how the universe works at the deepest level. Two big theories explain most of what we see: general relativity and quantum mechanics. General relativity explains how gravity works and describes large things like stars and galaxies. Quantum mechanics deals with tiny particles like atoms and electrons. Both theories work very well in their own areas, but they don't agree with each other. This is a problem because the universe doesn't separate into big and small parts. It's one thing, and scientists want a theory that explains everything. One possible solution comes from string theory. String theory says that the smallest building blocks of the universe aren't particles, like electrons, but tiny strings that vibrate. These strings are so small that we could never see them directly. The way the strings vibrate determines what kind of particle they make. A key part of string theory is that it requires extra dimensions to work. In fact, string theory suggests there are not 3, but 10 or even 11 dimensions. These extra dimensions could be curled up so small that we don't notice them, like tiny loops in a piece of thread. To understand how dimensions can be curled up, think about a garden hose lying on the ground. From far away, the hose looks like a straight line, but if you get closer, you see that it has a thickness and that you can move around its surface. The hose has more dimensions than you first thought. String theory says something similar could happen with space. The extra dimensions might be curled up so tightly that we don't notice them in our everyday lives. Another reason scientists consider extra dimensions is to explain why gravity is so weak. Compare gravity to the other fundamental forces, like electromagnetism, which powers electricity and magnets. Electromagnetism is much stronger than gravity. You can see this by picking up a paperclip with a magnet. A tiny magnet can overcome the gravity of the entire Earth pulling on the paperclip. Some scientists think gravity might seem weak because it spreads out into extra dimensions. If gravity can leak into these dimensions, it would explain why it feels so much weaker than the other forces. There have been experiments to test the idea of extra dimensions. One way to look for them is to measure gravity very precisely at small distances. If extra dimensions exist, gravity might behave differently at tiny scales. So far, these experiments haven't found evidence of extra dimensions, but they have set limits on how large the dimensions could be if they exist. Another place to look for extra dimensions is in particle accelerators, like the Large Hadron Collider in Europe. When particles smash into each other at high speeds, they create energy that could reveal the effects of extra dimensions. Scientists have looked for signs like missing energy, which might suggest particles escaping into an extra dimension. Again, they haven't found anything yet, but they are still looking. The idea of extra dimensions also appears in cosmology, the study of the universe as a whole. Some theories about the Big Bang suggest that extra dimensions played a role in creating the universe. Others propose that our universe is just one slice of a larger reality with more dimensions. If these ideas are correct, extra dimensions could help explain why the universe looks the way it does. It's worth noting that not everyone agrees on the need for extra dimensions. Some physicists think the theories that require them are too complicated or lack evidence. They argue that we should focus on ideas that can be tested more easily. Others point out that even if extra dimensions exist, they might not affect us in any measurable way, making them impossible to prove or disprove. Despite the challenges, the search for extra dimensions continues. It's a question that touches on some of the biggest mysteries in science, from the nature of gravity to the origin of the universe. If extra dimensions exist, they would change how we see the world and our place in it. They would show that what we think of as reality is just part of a much larger picture. In many ways, the idea of extra dimensions reminds us how much we still don't know. It's easy to think that we understand the world because we can describe so much of it, but the more we learn, the more questions we find. Extra dimensions might seem like a strange idea, but they show how scientists are willing to look beyond the obvious to find deeper truths about the universe. Whether or not they exist, the search for them pushes the boundaries of our understanding and opens the door to new possibilities. The fate of the universe is one of the most fascinating and mysterious topics in science. To understand it, we first need to grasp a few basic ideas about how the universe behaves. The universe is expanding. This discovery, first made by Edwin Hubble in the 1920s, means that galaxies are moving away from each other over time. If you imagine the universe as a balloon, the galaxies are like dots on its surface. As the balloon inflates, the dots move farther apart. This expansion gives us important clues about the future of everything around us. The rate of this expansion is a key factor in determining the universe's fate. Early on, scientists thought the expansion might slow down due to the gravitational pull of all the matter in the universe. This is similar to how a ball thrown into the air slows down because of Earth's gravity. For many years, They debated whether the universe would expand forever or eventually stop and collapse in on itself. A collapsing universe would end in what's called the Big Crunch, where everything gets pulled back together, potentially leading to another Big Bang. On the other hand, a universe that expands forever might cool down, with stars burning out and galaxies drifting apart, creating a cold, dark, and lifeless cosmos. In the late 1990s, scientists made a surprising discovery that changed our understanding of this question. By observing distant supernovae, they found that the universe's expansion is not slowing down but speeding up. This acceleration suggested the existence of a mysterious force pushing galaxies apart. Scientists named this force dark energy. Although we don't fully understand dark energy, it seems to make up about 70% of the universe. It plays a crucial role in shaping the cosmos and its destiny. The acceleration of the universe's expansion introduces new possibilities for its ultimate fate. One scenario is known as the Big Freeze. In this outcome, the universe continues to expand indefinitely. Over billions of years, galaxies will move so far apart that they become isolated, and the night sky will grow dark. Stars will eventually run out of fuel and stop shining. The universe will become a cold, empty space filled with dead stars, black holes, and faint radiation. This process could take an unimaginably long time, but it paints a bleak picture of a universe that slowly fades into nothingness. Another possibility, called the Big Rip, depends on the behavior of dark energy. If dark energy becomes stronger over time, it could tear the universe apart. In this scenario, the acceleration of expansion would increase so much that it would overcome gravity and other forces holding objects together. Galaxies, solar systems, and even atoms could be ripped apart in the final moments. The Big Rip would result in a violent and chaotic end, with everything in the universe torn to shreds. There's also a scenario where dark energy could weaken or even reverse. In this case, the universe might stop expanding and begin to contract. This is where the idea of the Big Crunch comes back into play. If gravity overcomes the push of dark energy, the universe could collapse back into a dense, hot state. Some scientists speculate that this might lead to another Big Bang, creating a cyclic universe that expands and contracts endlessly. While this idea is intriguing, current evidence supports the idea of continued expansion, making the Big Crunch less likely. Another theoretical possibility involves the quantum nature of the universe. Quantum mechanics suggests that space and time have a fundamental underlying structure. This structure might not be completely stable. Over incredibly long timescales, a phenomenon called vacuum decay could occur. This would involve a tiny bubble of a more stable quantum state appearing in the universe. If this bubble formed, it could expand at the speed of light, destroying everything in its path. While this idea sounds dramatic, it's based on speculative physics and is far from certain. To make sense of these scenarios, it helps to think about the universe as a complex system governed by a few key forces and constants. Gravity, dark energy, and the properties of matter all interact in ways that shape the cosmos. Even small changes in these factors could lead to very different outcomes. For example, if dark energy behaves slightly differently than we expect, the future of the universe could change drastically. The ultimate fate of the universe also raises philosophical questions. If the universe ends in a big freeze or a big rip, does that mean all life and knowledge are doomed to disappear? On the other hand, if the universe cycles through big bangs and big crunches, could life or even civilizations exist in future versions of the cosmos? These questions remind us that understanding the universe's fate is not just a scientific challenge, but also a deeply human one. Observing the universe today helps scientists gather clues about its future. By studying the motion of galaxies, the properties of dark energy, and the behavior of black holes, they can refine their predictions. For instance, missions like the James Webb Space Telescope aim to study the early universe in greater detail, helping us understand how it has evolved over billions of years. Every new discovery brings us closer to unraveling the mysteries of the cosmos. Even though we don't know the exact fate of the universe, our exploration of this question reveals the beauty and complexity of the natural world. It shows us how small changes in the forces and constants of nature can lead to profound outcomes. Whether the universe ends in a big freeze, a big rip, or something else entirely, the journey of discovery is a reminder of humanity's deep curiosity and our ability to ask big questions. Consciousness is one of the most fascinating and mysterious aspects of human experience. It's what allows you to feel, think, and be aware of your surroundings and yourself. When you hear the sound of a bird or feel the warmth of the sun on your skin, you are experiencing consciousness. But despite being such an essential part of life, scientists and philosophers struggle to explain what consciousness actually is and how it works. At its core, consciousness is about awareness. It's the state of being awake and able to interact with the world. It's not just about sensing things around you, but also about knowing that you are sensing them. For instance, when you smell a flower, your brain processes the scent, but your mind also registers that you are the one smelling it. That self-awareness is a key part of consciousness. Many people think of consciousness as something only humans have, but animals also show signs of awareness. A dog wagging its tail in response to your voice, or a cat curling up in your lap, suggests that these creatures are experiencing something similar to consciousness. They react to their environment, and they appear to have emotions and preferences. However, their consciousness may not be the same as ours. Human consciousness involves not only awareness, but also a sense of identity and the ability to reflect on thoughts and feelings. You can think about what you did yesterday or plan for tomorrow, and you can question why you feel a certain way. That level of introspection seems unique to humans, at least as far as we know. The brain plays a central role in consciousness. Most scientists agree that consciousness arises from the brain, but how that happens is still unclear. The brain is made up of billions of neurons, and these neurons communicate with each other through electrical signals. This network of connections allows us to process information, make decisions, and form memories. But there's a big gap between understanding how neurons work and explaining how they create the feeling of being alive and aware. To explore this gap, scientists have studied what happens to consciousness when the brain changes. For example, when someone is under anesthesia, they lose consciousness. They can't feel pain or hear sounds, and they won't remember anything that happens during that time. This suggests that consciousness depends on certain parts of the brain being active. Similarly, people with brain injuries sometimes lose specific aspects of consciousness. A person with damage to the visual part of the brain might lose the ability to see, even though their eyes still work. These cases show that consciousness is closely tied to brain function. One area of the brain that seems especially important for consciousness is the cerebral cortex. This outer layer of the brain is involved in higher-level processes like thinking, planning, and decision-making. Different regions of the cortex are responsible for different types of awareness. For instance, the visual cortex processes information from your eyes, while the auditory cortex handles sounds. The brain's ability to integrate information from all these regions may be what allows us to experience the world as a unified whole. But understanding which parts of the brain are involved in consciousness doesn't explain why we feel conscious in the first place. This is sometimes called the hard problem of consciousness. It's one thing to say that neurons in the brain fire in response to light or sound, but it's another to explain why that firing leads to the experience of seeing a sunset or hearing a song. This question has puzzled thinkers for centuries, and it remains a major challenge for modern science. Some researchers believe that consciousness might emerge from the complexity of the brain. They argue that when a system becomes complex enough, like the human brain, consciousness arises as a natural byproduct. This idea is similar to how life emerges from non-living molecules. At a certain level of complexity, those molecules start working together to form a living organism. Perhaps consciousness is a similar kind of phenomenon, but instead of arising from molecules, it arises from information processing in the brain. Others think that consciousness might be a fundamental part of the universe, like space or time. This view is called panpsychism, and it suggests that everything in the universe has some basic level of consciousness, even if it's very simple. According to this idea, a rock or a tree wouldn't have thoughts or feelings like we do, but it might have a tiny, almost imperceptible awareness. Human consciousness, in this view, would be a more advanced version of this basic awareness. Another perspective comes from artificial intelligence. Some scientists are trying to create machines that can think and learn like humans. This raises the question of whether a machine could ever become conscious. If a computer could process information in the same way as the human brain, would it feel aware of itself? So far, no artificial system has shown clear signs of consciousness, but the possibility challenges our understanding of what it means to be conscious. Consciousness is also shaped by culture and language. The way you think about yourself and the world depends in part on the words you use and the ideas you've been exposed to. For example, some cultures have words for emotions that don't exist in other languages, which might influence how people in those cultures experience those emotions. This shows that consciousness isn't just a biological phenomenon, but also a social one. Your interactions with other people and the culture you live in shape your awareness and understanding of the world. Despite all the research and debate, there's still no single answer to the question of what consciousness is. It might be one of those mysteries that humans can only partially understand. But studying consciousness helps us learn more about ourselves and the nature of life. It also raises important ethical questions, like how we should treat animals, or whether machines deserve rights if they become conscious. Think about the simple act of watching a sunset. You see the colors of the sky, you feel the temperature drop as the sun sets, and you might even feel a sense of peace or wonder. These experiences are deeply personal, and they remind us of what it means to be alive. Consciousness allows us to connect with the world and with each other, making it one of the most profound aspects of human existence. While we may not have all the answers, exploring consciousness gives us a better understanding of who we are and our place in the universe. Consciousness is one of the most intriguing topics in science and philosophy. When we think of consciousness, we often think about humans being aware of their thoughts, feelings, and surroundings. But when we extend the idea to non-human animals or machines, the picture becomes less clear. Understanding whether animals and machines possess consciousness requires exploring how we define it and how it might manifest in beings that are very different from us. When people discuss consciousness in animals, they often focus on whether animals experience emotions or perceive their environment in a way that resembles humans. For example, many pet owners might say their dog seems happy when wagging its tail, or sad when left alone. These behaviors suggest some level of awareness, but they don't necessarily prove that animals experience emotions the same way humans do. This is because emotions, as we understand them, are tied to subjective experiences, things like joy, fear, or sadness, which are hard to measure in another being. Scientists studying animal consciousness often look for evidence of self-awareness, which is sometimes tested using experiments like the mirror test. In the mirror test, researchers place a mark on an animal's body in a location the animal can't see without a mirror. If the animal looks in the mirror and tries to touch or remove the mark on its own body, this suggests it recognizes itself in the reflection. Some animals, like chimpanzees, dolphins, and elephants, pass this test. They seem to realize that the image in the mirror is not another animal, but themselves. This self-recognition is one potential indicator of consciousness, but it isn't the whole story. Other animals, like dogs or cats, usually fail the mirror test. However, this doesn't mean they lack consciousness. It might mean they don't rely on vision as much as humans do to understand their surroundings, or that the test doesn't measure the kind of awareness they have. Beyond self-awareness, some researchers argue that many animals demonstrate forms of consciousness through their behaviors. For instance, certain birds, like crows and parrots, can solve complex problems and even use tools. In one experiment, a crow was given a puzzle that required multiple steps to solve. The bird figured out how to use a smaller tool to retrieve a larger tool, and then use that larger tool to access food. This level of problem solving suggests an ability to think ahead and adapt, which are hallmarks of consciousness. Similarly, some studies show that octopuses exhibit playful behavior. like interacting with objects in their environment in ways that don't directly serve a survival purpose. These observations hint that consciousness in animals might exist on a spectrum, with some species showing more complex forms of awareness than others. When it comes to machines, the question of consciousness becomes even more complicated. Machines, particularly artificial intelligence systems, are designed by humans to perform specific tasks. Some of these tasks might mimic human thought processes, like recognizing patterns, solving problems, or even generating human-like text. However, doing something that looks like thinking isn't the same as actually thinking. Consciousness, as most people understand it, involves subjective experience, an inner awareness that machines currently do not possess. To illustrate this, consider a simple example. When you use a voice assistant on your phone, it might respond to your question about the weather or play your favorite song. The software analyzes your request, matches it with stored data, and provides an appropriate response. But the machine isn't aware of what it's doing. It doesn't know it's interacting with you or understand the concept of weather or music. It's simply following its programming, even though the result might feel human-like. Some advanced AI systems, like those used in natural language processing or image recognition, can seem even more intelligent. These systems can analyze vast amounts of data, identify patterns, and produce outputs that might surprise even their creators. For example, some AI systems can generate art or write stories that people find creative. But this creativity is not the same as human creativity. Humans create based on feelings, ideas, and experiences, while machines generate outputs based on algorithms and data. The machine doesn't feel proud of its work or understand the meaning behind it. Still, some researchers suggest that consciousness in machines might one day be possible. If consciousness arises from the complexity of a system, as some theories propose, then a sufficiently advanced machine might achieve something like awareness. For example, if the brain is a network of neurons exchanging electrical signals, and if consciousness emerges from that network's complexity, could a machine with an equally complex network of artificial neurons develop a similar awareness? This idea remains speculative, as we don't fully understand how consciousness works even in humans. Without that understanding, it's difficult to say whether it could ever be replicated in a machine. One challenge in determining whether animals or machines have consciousness is that we can't directly observe or measure subjective experience. We know what it feels like to be conscious because we experience it ourselves, but we can't step into the mind of another being, animal or machine, to know if they experience something similar. Instead, we rely on external behaviors and evidence, like problem solving or communication, to make inferences. But this approach has its limits. A machine might mimic human behavior without actually having any awareness, and an animal might experience consciousness in ways that don't manifest through behaviors we recognize. Imagine, for example, a robot that passes the mirror test because it's programmed to respond to its reflection in a certain way. From the outside, it might look like the robot is self-aware, but it's simply following instructions. On the other hand, a dog failing the mirror test might still have a rich inner life of smells, sounds, and emotions that we can't easily measure or understand. These scenarios show the complexity of defining and identifying consciousness, especially in beings very different from humans. Another layer to this question is the ethical implications. If some animals are conscious, should we treat them differently? Many people already believe that animals like primates, dolphins, and elephants deserve special protection because of their intelligence and potential awareness. If we ever build machines that are truly conscious, we might face similar ethical dilemmas. For instance, would turning off a conscious machine be equivalent to causing harm or ending a life? These questions are currently theoretical, but they highlight the importance of understanding consciousness in all its forms. In summary, whether non-human animals and machines have consciousness depends on how we define and recognize it. Animals exhibit behaviors that suggest varying levels of awareness, from self-recognition to problem-solving and emotional responses. Machines, meanwhile, can mimic intelligent behaviors but lack subjective experience. The mystery of consciousness remains one of the biggest challenges in science and philosophy, and it's possible that the answers will require us to rethink our assumptions about what it means to be aware. As we learn more, we may discover that consciousness is not an all-or-nothing trait, but something that exists in different forms across species and systems. The question of how life began on Earth has puzzled scientists, philosophers, and curious minds for centuries. Understanding the origins of life requires us to explore a time billions of years ago when our planet was nothing like the world we know today. It was a harsh, alien environment with no plants, animals, or people. Yet from that hostile landscape, life somehow emerged. The mystery is not only about where life came from, but also how inanimate molecules could assemble themselves into something living. To approach this question, we must piece together evidence from chemistry, biology, geology, and physics. The Earth formed around 4.5 billion years ago. Early on, it was a molten ball of rock, constantly bombarded by asteroids and comets. Over time, the surface cooled, forming a crust, and water collected to create oceans. This setting became a stage for chemical reactions that might have led to life. Scientists believe the conditions on early Earth were crucial for this process. The planet had a mix of water, energy sources like sunlight and lightning, and an atmosphere with simple gases such as methane, ammonia, hydrogen, and carbon dioxide. These ingredients could have interacted to form the building blocks of life. One of the most famous ideas about how life began comes from an experiment in the 1950s. Two scientists, Stanley Miller and Harold Urey, wanted to test if the chemicals in Earth's early atmosphere could produce organic molecules. They mixed gases like methane and ammonia in a closed system, added water to mimic oceans, and used electric sparks to simulate lightning. After a week, they found that the experiment had produced amino acids, which are the building blocks of proteins. This result was groundbreaking because it showed that simple chemicals could combine to form more complex molecules under the right conditions. However, amino acids alone are not life, so the next step is figuring out how they came together to create something living. Life is made of cells, and at their core, cells rely on molecules like proteins, DNA, and RNA. These molecules do different jobs that keep life going. Proteins are like tiny machines that perform tasks in the cell, while DNA and RNA store and transmit information. One challenge in understanding the origin of life is determining which came first. Did proteins form first and then help create DNA and RNA? Or did RNA come first because it can both store information and perform simple tasks like proteins? This debate has led to theories about an RNA world, where RNA molecules might have been the earliest form of life. RNA can copy itself, carry genetic information, and even act as a catalyst for chemical reactions. If RNA formed on early Earth, it might have been a stepping stone toward life. But how could molecules like RNA or proteins form naturally without help? This is where scientists look to chemistry and geology for answers. For instance, some researchers think that certain environments on early Earth could have acted like natural laboratories. Hydrothermal vents on the ocean floor are one example. These vents release hot, mineral-rich water from beneath the Earth's crust, creating conditions that could support the formation of complex molecules. Another possibility is that shallow ponds or clay surfaces on land might have concentrated organic molecules, making it easier for them to interact and form larger structures. These scenarios show how specific environments could have played a role in the first steps toward life. Once the building blocks of life formed, the next challenge was organizing them into something more complex. In modern life, cells have membranes that keep their contents separate from the outside world. This separation is essential because it allows cells to maintain the conditions they need to survive and grow. Scientists believe that simple versions of membranes could have formed naturally. Fatty molecules, which are common in living organisms, can spontaneously arrange themselves into structures like bubbles when they are in water. These bubbles could trap other molecules inside, creating a tiny environment where chemical reactions could occur. If these reactions help the bubble grow or divide, it might be considered a very early form of life. Even with these pieces in place, the leap from chemistry to biology remains one of the biggest mysteries. Life isn't just about having the right molecules, it's about those molecules working together in a self-sustaining way. For something to be alive, it must grow, reproduce, and evolve. Scientists think that evolution might have started at the molecular level. For example, if an RNA molecule made copies of itself, some copies might have been slightly better at surviving or reproducing than others. Over time, these small differences could lead to more complex and efficient systems. This idea ties the origin of life to the same process that drives evolution in all living things today. Another intriguing idea is that life might not have started on Earth at all. Some scientists suggest that the building blocks of life could have come from space. Meteorites and comets often contain organic molecules, including amino acids. If these molecules landed on Earth, they could have contributed to the chemical reactions that led to life. This idea, called panspermia, doesn't solve the mystery of how life began, but it raises the possibility that the ingredients for life are common in the universe. The question of how life originated is not just about understanding the past. It also helps us think about the possibility of life elsewhere. If life emerged from simple chemicals on Earth, then similar processes might happen on other planets or moons with the right conditions. For example, Jupiter's moon Europa and Saturn's moon Enceladus have subsurface oceans that could harbor life. Mars once had liquid water on its surface, and scientists are still exploring whether it might have hosted life in the past. By studying how life began on Earth, we can better understand what to look for as we search for life beyond our planet. Despite decades of research, we don't have all the answers. Scientists are still testing different ideas and looking for clues in ancient rocks, laboratory experiments, and even other planets. The origin of life is a puzzle with many missing pieces, but each discovery brings us closer to understanding how the incredible diversity of life on Earth began. The search is far from over, but it is a reminder of how much we still have to learn about our own existence. Life's beginnings remain one of the most profound and fascinating mysteries in science, connecting us to the chemistry of the universe and the conditions of our ancient world. For as long as humans have looked up at the stars, we have wondered if we are alone in the universe. The question is as much a philosophical one as it is scientific. When you consider the vastness of space and the countless stars and planets that exist, it seems almost unthinkable that Earth is the only place where life has emerged. Yet, despite decades of searching, we still lack clear evidence of life beyond our planet. Scientists, however, continue to approach the question with both curiosity and careful methods, trying to find answers in the data we gather from space and through the experiments we conduct here on Earth. One way to think about this question is to examine the conditions that allowed life to develop on Earth. Our planet has liquid water, an atmosphere that protects us from harmful radiation, and the right chemical ingredients like carbon, hydrogen, and oxygen to support living organisms. Earth also orbits in what scientists call the habitable zone around the Sun. This means it is not too hot or too cold for liquid water to exist, which many believe is a key ingredient for life. If life depends on these conditions, then the search for extraterrestrial life often focuses on planets that share similar traits. Our galaxy, the Milky Way, is enormous. It contains around 100 billion stars, many of which have planets orbiting them. Some of these planets may be Earth-like, meaning they are rocky, roughly the same size as Earth, and located in their star's habitable zone. The Kepler Space Telescope, which searched for planets beyond our solar system, identified thousands of these exoplanets. Of these, a few appear to have conditions that might allow life to exist. But identifying a potentially habitable planet and proving it hosts life are two very different challenges. When scientists talk about the search for life, they usually divide it into two categories: microbial life and intelligent life. Microbial life would be simpler organisms like bacteria, which could potentially exist under a wide range of conditions. Intelligent life, on the other hand, refers to beings capable of advanced thought, communication, and perhaps even space exploration. If we ever discover life beyond Earth, most scientists believe it is far more likely to be microbial. This is because simple organisms are more adaptable and can survive in extreme environments, like deep under the ocean or in the freezing cold of Antarctica, where more complex life would struggle. Mars has long been a focus of our search for microbial life. Its surface shows signs that it once had flowing rivers and lakes, and recent discoveries suggest that underground reservoirs of liquid water may still exist. Rovers like Perseverance and Curiosity are exploring the planet, collecting samples and analyzing the soil for signs of life. While we haven't found definitive proof yet, Mars remains one of the best places to look for past or present life in our solar system. Beyond Mars, scientists are interested in the icy moons of Jupiter and Saturn. Europa, a moon of Jupiter, has a thick ice shell, but beneath it lies an ocean of liquid water. This ocean is kept warm by heat generated as Europa is squeezed and stretched by Jupiter's gravity. Enceladus, a moon of Saturn, also has a subsurface ocean. It even shoots water vapor into space through cracks in its surface, which spacecraft like Cassini have analyzed. These findings show that the ingredients for life could exist in places we once thought were too hostile. The search for intelligent life takes a different approach. Projects like SETI, the search for extraterrestrial intelligence, use powerful radio telescopes to listen for signals from other civilizations. The idea is that if intelligent beings exist elsewhere, they might also be trying to communicate. Radio waves are a good medium for this because they travel long distances through space without losing much strength. Over the years, SETI has listened to millions of frequencies, hoping to pick up a message that could not have come from natural sources. So far, nothing conclusive has been detected, but the search continues. Another way we might detect intelligent life is by looking for technosignatures. These are signs of advanced technology, like the glow of city lights on a planet's surface, unusually high levels of industrial chemicals in an atmosphere, or massive structures that block the light from a star. For example, a theoretical concept called a Dyson sphere suggests that a highly advanced civilization might build a structure around its star to capture energy. If we noticed a star dimming in a way that couldn't be explained naturally, it might be evidence of such a structure. Of course, there are many reasons why we might not have found evidence of extraterrestrial life yet. The distances involved are immense, making communication or travel incredibly difficult. Even our closest star system, Alpha Centauri, is over 4 light-years away. If we sent a signal there today, it would take over 4 years to arrive, and another 4 years to get a response. It's also possible that intelligent life is rare, short-lived, or uninterested in making contact. Civilizations might develop technology and then self-destruct through war or environmental destruction before they can explore the galaxy. Another possibility is that life exists in forms we do not recognize. On Earth, life is based on carbon and relies on water, but there's no guarantee that life elsewhere would follow the same rules. Some scientists speculate about silicon-based life forms or organisms that thrive in environments we consider hostile, such as the methane lakes on Titan, Saturn's largest moon. If extraterrestrial life is too different from what we know, we might not even recognize it as living. The absence of evidence for extraterrestrial life has led some people to embrace the idea that we might indeed be alone. This perspective is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If the galaxy is full of stars and planets, and if life is common, why haven't we seen any signs of it? Some propose that advanced civilizations might avoid contact with others, much as isolated tribes on Earth have sometimes avoided outsiders. Others think we might be looking in the wrong way, or that the universe is simply too vast for us to notice one another. The search for life beyond Earth isn't just about answering a question, it's about understanding our place in the universe. If we find even a single microbe on another planet, it would mean that life is not unique to Earth. It would suggest that life could emerge in many places, under many conditions. If, on the other hand, we find no evidence of life after searching thoroughly, it would highlight just how rare and precious life on Earth truly is. Either outcome carries profound implications for how we see ourselves and our future. For now, we can only keep searching, using the tools and knowledge we have, and remain open to the idea that the universe might still surprise us. In the end, the question of whether we are alone may remain one of the greatest mysteries of all time. But even as we search for an answer, we are learning more about the universe and our own planet, enriching our understanding of existence itself. Life on Earth began as simple, single-celled organisms billions of years ago. These organisms were relatively straightforward in their structure and function, capable of surviving in the challenging conditions of early Earth. Over time, something extraordinary happened. These simple cells gave rise to complex, multicellular life forms. Understanding how this transformation occurred is one of biology's most fascinating puzzles. Scientists have pieced together key steps in this process, offering insights into how tiny, independent cells began working together to form the complex creatures we see today. Imagine a microscopic world filled with individual cells, each living its own life. These cells were prokaryotic, meaning they lacked a defined nucleus. Some of them were bacteria, while others belonged to a group called archaea. Over millions of years, certain cells evolved more complex structures, becoming what we now call eukaryotic cells. These cells had a nucleus to store their genetic material and specialized compartments called organelles for different tasks. The evolution of eukaryotic cells was a critical step because it provided a foundation for greater complexity. One widely accepted theory about this leap involves a process called endosymbiosis. In this scenario, a larger cell engulfed smaller cells, such as bacteria, without digesting them. Instead of competing, the two organisms formed a mutually beneficial relationship. The smaller cells provided energy or other resources, while the larger cell offered protection. Over time, the smaller cells became permanent parts of the larger cell, evolving into organelles like mitochondria and chloroplasts. These organelles play vital roles in energy production and photosynthesis, which were essential for supporting larger, more complex life forms. Once eukaryotic cells emerged, the stage was set for multicellularity. The first multicellular organisms were likely simple clusters of identical cells. These clusters formed when individual cells stayed connected after dividing. Living in groups offered certain advantages. For example, a cluster could be more resistant to predators than a single cell. Some cells in the group might specialize in specific functions, like moving or gathering food, making the whole group more efficient. This division of labor was an important step toward complexity. An example of this kind of transition can be seen in modern organisms like Volvox, a type of green algae. Volvox forms colonies of cells that work together. Some cells in the colony focus on reproduction, while others handle movement. This arrangement shows how simple multicellular structures can evolve when individual cells cooperate. Such cooperation likely began billions of years ago, as cells found ways to communicate and coordinate their activities. Communication between cells was a turning point in the evolution of multicellularity. For cells to work together, they needed to exchange information. Chemical signals allowed cells to communicate, sending messages about growth, division, and other vital processes. Over time, cells developed more sophisticated signaling pathways, enabling complex coordination. For instance, in animal bodies today, hormones and neurotransmitters carry messages between different tissues and organs, ensuring that the whole organism functions as a unit. Cell adhesion was another critical development. Cells needed to stick together to form stable structures. This required specialized proteins that acted like glue, holding cells in place. Once cells were able to adhere reliably, they could form tissues, which are groups of cells working together for a specific purpose. For example, muscle tissue allows animals to move, while vascular tissue in plants transports water and nutrients. These specialized tissues laid the groundwork for the development of organs and eventually entire organ systems. The fossil record gives us glimpses of early multicellular life. Some of the earliest examples include tiny fossils from about 1.6 billion years ago that show simple clusters of cells. Around 600 million years ago, during a period known as the Ediacaran, larger and more complex multicellular organisms appeared. These organisms had soft bodies and included forms that resembled modern jellyfish, worms, and corals. They likely relied on simple diffusion to get oxygen and nutrients, limiting their size and complexity. However, they represented an important step in the evolution of life. A major breakthrough came during the Cambrian explosion, about 540 million years ago. During this period, an incredible variety of multicellular organisms emerged in a relatively short time. These organisms had diverse body plans, with specialized structures like shells, limbs, and eyes. The Cambrian explosion marked the first appearance of many of the major groups of animals we know today, such as arthropods, mollusks, and vertebrates. It was a time of rapid innovation, fueled by changes in the environment like increased oxygen levels and by the evolution of genetic tools that allowed for greater complexity. The genetic toolkit that enabled multicellular life is another fascinating aspect of this story. Genes control how organisms develop and function. Certain genes, known as regulatory genes, play a key role in shaping body plans. For example, Hox genes determine the placement of body parts, such as legs, wings, and antennae, in animals. These genes are highly conserved, meaning they have remained similar across different species for hundreds of millions of years. The evolution of regulatory genes allowed for the development of complex structures and body plans, paving the way for the diversity of life we see today. Even with all these advances, multicellular life still faced challenges. For multicellularity to succeed, cells had to suppress selfish behavior. If one cell in a group started acting in its own interest, it could harm the whole organism. For example, cancer occurs when cells in a multicellular organism begin dividing uncontrollably, ignoring the signals that regulate growth. To prevent this, multicellular organisms evolved mechanisms to control cell behavior, like programmed cell death, which eliminates malfunctioning cells before they cause problems. Over billions of years, the evolution of complex multicellular life transformed the planet. Simple cells that once floated in the oceans gave rise to plants, animals, and fungi, each with remarkable adaptations. Plants developed ways to harness sunlight through photosynthesis, producing oxygen and shaping the Earth's atmosphere. Animals evolved nervous systems and muscles, enabling movement and interaction with their environment. Fungi played a crucial role in breaking down organic material, recycling nutrients, and forming symbiotic relationships with plants. Today, multicellular organisms dominate life on Earth, but they owe their existence to the early steps taken by single-celled ancestors. The journey from simple clusters of cells to the intricate ecosystems we see now was driven by innovation, cooperation, and adaptation. By studying this process, scientists continue to uncover the fundamental principles of life and evolution, deepening our understanding of the natural world. The term junk DNA refers to portions of our genetic material that don't seem to have a clear function. Scientists first used this term decades ago when they noticed large sections of DNA that didn't code for proteins, which are the building blocks of cells and carry out most of the work in our bodies. At the time, it seemed reasonable to think these non-coding regions were useless leftovers, evolutionary baggage with no purpose. But over the years, researchers have found clues that suggest this DNA isn't really junk at all. Instead, these sections might play subtle yet crucial roles in how our genes work, how we develop, and even how diseases take hold in our bodies. To understand why people thought of this DNA as junk, it helps to know what DNA does. DNA is a long molecule packed tightly into chromosomes inside the cells of your body. Each strand of DNA carries instructions in the form of genes. A gene is a section of DNA that provides the recipe for making a specific protein. Proteins, in turn, are responsible for many of the body's functions, like repairing tissues, sending chemical signals, and fighting off infections. When researchers first started studying DNA, they focused on the genes that code for these proteins. They assumed these genes were the most important part of DNA because they had such obvious jobs. But then they discovered something surprising. Most of the DNA in the human genome doesn't code for proteins. In fact, protein-coding DNA makes up less than 2% of our entire genome. This raised a big question. If only a tiny fraction of our DNA codes for proteins, what is the rest doing? At first, scientists couldn't find any answers. Much of this non-coding DNA seemed to sit there, silent and inactive. Without evidence to suggest a purpose, researchers started calling it junk DNA. It wasn't meant to be dismissive, it was just a way to describe what they didn't yet understand. As time went on, this label began to feel too simplistic. Advances in genetics and molecular biology revealed that many parts of non-coding DNA do have functions, though these roles are often indirect or hard to measure. One of the first big discoveries involved regulatory sequences. These are stretches of DNA that don't make proteins but help control when and where other genes are turned on or off. Think of them like switches or dimmers in an electrical circuit. They help ensure that the right genes are active in the right cells at the right times. For example, a regulatory sequence might ensure that a gene involved in muscle growth only turns on in muscle cells and not in nerve cells. Another important role for non-coding DNA involves RNA. While DNA is often thought of as a blueprint for proteins, it also serves as a template for making RNA. RNA is a molecule similar to DNA, but it's more versatile. Some RNA molecules carry instructions from DNA to the protein-making machinery in cells, but others have roles that don't involve proteins at all. For instance, some RNA molecules help regulate gene activity, and others play structural or catalytic roles. Many of these RNA molecules are encoded in the so-called junk DNA. A fascinating example of how non-coding DNA can have hidden purposes comes from studying repetitive DNA sequences. These are short stretches of DNA that repeat over and over again in the genome. For a long time, scientists thought these sequences were useless, but recent research suggests they might help organize chromosomes within the cell. Chromosomes aren't just jumbled together randomly. They occupy specific territories in the nucleus, and repetitive sequences may play a role in maintaining this order. This spatial organization can influence which genes are active, adding another layer of control to how the genome works. Another clue about the importance of non-coding DNA comes from comparing genomes across different species. If a piece of DNA really is junk, you'd expect it to accumulate random mutations over time without any consequences. But some parts of non-coding DNA are highly conserved, meaning they've stayed nearly identical across millions of years of evolution. This suggests these regions are important, even if we don't fully understand why. For example, some conserved non-coding regions seem to act as enhancers, boosting the activity of nearby genes. Others may help stabilize the genome, preventing harmful mutations or structural changes. Non-coding DNA also appears to have a role in shaping the immune system. Our immune system needs to adapt to fight a wide variety of infections, and some of this adaptability comes from non-coding DNA. For instance, certain non-coding regions help generate the diversity of antibodies that the body can produce. This diversity is crucial for recognizing and attacking different pathogens. Without these non-coding sequences, our immune system wouldn't be nearly as effective. Understanding the roles of non-coding DNA has practical implications for medicine. Many diseases, including cancer, heart disease, and neurological disorders, are influenced by changes in non-coding DNA. For instance, mutations in regulatory sequences can disrupt the normal activity of genes, leading to uncontrolled cell growth or other problems. By studying non-coding DNA, scientists hope to identify new targets for treatments or even predict who might be at risk for certain conditions. There's also growing evidence that non-coding DNA might influence traits we think of as uniquely human, like brain development and behavior. Some researchers believe that subtle changes in non-coding regions help drive the evolution of our species, allowing for more complex brains and advanced cognitive abilities. These changes may have affected how genes are expressed during development, shaping the intricate networks of cells in the brain. While we've learned a lot about non-coding DNA, there's still much more to discover. Many regions of the genome remain poorly understood, and it's likely that some parts of non-coding DNA really are useless, at least in the sense that they don't have an active role today. But even if some of it is truly junk, dismissing all non-coding DNA as unimportant would be a mistake. The history of genetics is full of examples where scientists initially underestimated the complexity of the genome, only to discover later that it was more intricate than they imagined. It's also worth remembering that the term junk DNA reflects more about our understanding than the DNA itself. When scientists can't see a clear purpose for something, it's easy to assume it doesn't matter. But the natural world often works in ways that are subtle, redundant, or layered. and what seems unnecessary at first glance might turn out to be essential when viewed from a different angle. Non-coding DNA is a reminder that science is a process of continual discovery, and what we think we know is always subject to change as new evidence comes to light. So while we don't have all the answers yet, one thing is clear: calling it junk doesn't do it justice. Non-coding DNA is a vast, largely uncharted territory, and exploring it will likely reveal new insights into what makes us who we are, how we stay healthy, and what goes wrong when diseases arise. There's a lot we still don't know, but that's what makes it such an exciting area of research. Epigenetic factors shape organisms by influencing how their genes work without changing the actual DNA sequence. To understand this, think of the genome, the complete set of DNA in an organism, as a vast library of instructions. Every cell in the body has access to the entire library, but it doesn't use all the books at once. Epigenetics helps decide which books get opened and which stay closed in each cell. This process ensures that a skin cell doesn't act like a brain cell, or vice versa. Epigenetic changes determine which genes are active, shaping how a cell functions and ultimately how an organism develops and responds to its environment. One of the main ways epigenetics works is through chemical tags that attach to DNA or the proteins around which DNA is wound. Imagine a book in the library that has sticky notes marking certain chapters. These sticky notes don't change the words in the book, but they tell you which sections to read and which to skip. In the genome, a common type of tag is called a methyl group. When a methyl group attaches to a part of DNA, it often blocks the gene from being read. This process, called DNA methylation, can silence a gene that might otherwise be active. By contrast, removing these tags can allow the gene to be read again. The proteins that help package DNA, called histones, also play a role. DNA wraps around histones, and the way it wraps affects whether the DNA is accessible for reading. Picture a spool of thread. If the thread is wound too tightly, it's hard to pull out a section. Similarly, when DNA is tightly wound around histones, the genes in that section may be inaccessible. Epigenetic factors can modify histones, loosening or tightening the DNA and controlling which genes are accessible. Epigenetic changes are essential during development. At the start of life, a single fertilized egg cell divides into many cells, and these cells specialize into types like muscle cells, nerve cells, or blood cells. Even though all these cells have the same DNA, they perform very different tasks. Epigenetics makes this possible. It turns on the genes needed for a cell's specific job and silences the rest. For instance, a muscle cell might activate genes that produce proteins for movement while silencing genes used by brain cells. The environment also influences epigenetics. Factors like diet, stress, and exposure to toxins can change the chemical tags on DNA and histones. These changes can affect how genes work, sometimes in ways that improve survival. For example, consider a plant that experiences drought. Epigenetic changes might activate genes that help the plant conserve water. If the drought lasts long enough, these changes can be passed to the next generation, giving the offspring a better chance to survive similar conditions. One striking example of epigenetics in action is the effect of maternal care on offspring. In studies with rats, researchers found that pups nurtured by attentive mothers showed different patterns of DNA methylation compared to pups raised by less attentive mothers. These changes affected genes involved in stress response. Pups from attentive mothers grew up to handle stress better, while those from less attentive mothers became more anxious. These differences weren't due to changes in the DNA sequence, but to epigenetic modifications influenced by early life experiences. Epigenetics also plays a role in disease. For instance, cancer often involves changes in the normal patterns of DNA methylation. Some genes that suppress tumor growth become silenced, while others that promote cell division become overly active. Understanding these changes helps researchers develop targeted therapies. Drugs that modify epigenetic tags can reactivate silenced genes or quiet overactive ones, offering new ways to treat cancer. Another area where epigenetics is important is aging. Over time, the pattern of chemical tags on DNA changes, and these changes can influence how well cells function. Some researchers believe that reversing certain epigenetic changes could slow aging or reduce the risk of age-related diseases. For example, in studies with mice, scientists have shown that altering epigenetic marks can improve physical health and extend lifespan. Epigenetic changes can also be passed from one generation to the next, a process known as transgenerational epigenetic inheritance. This means that experiences or environmental exposures in one generation can affect the health and traits of future generations. For instance, studies in humans have suggested that famine during a grandparent's childhood can influence the risk of diseases like diabetes in their grandchildren. While this area of research is still evolving, it highlights how deeply interconnected genes, environment, and epigenetics are. To understand how epigenetics shapes organisms, think of identical twins. They share the same DNA, yet they often show differences as they age. These differences can include traits like height, weight, or susceptibility to diseases. Epigenetics helps explain this. Over time, twins experience different environments, diets, and stress levels. These differences influence their epigenetic patterns, leading to variations in gene activity and ultimately in their physical traits and health. Scientists are just beginning to uncover the full impact of epigenetics. It's clear that it acts as a bridge between genes and the environment, shaping how organisms grow and adapt. While the DNA sequence provides the instructions, epigenetic factors decide when and where those instructions are used. This dynamic system allows organisms to respond to their surroundings and ensures that cells work together in harmony. The more we understand epigenetics, the better we can tackle complex questions about health, development, and evolution. Quantum mechanics and general relativity are two of the most successful theories in physics. They explain the world in ways that are consistent with observations and experiments. Quantum mechanics describes the smallest scales of reality, such as atoms and particles. General relativity, on the other hand, explains the behavior of massive objects like stars, planets, and even the universe itself. Despite their successes, these two theories do not work well together. This lack of harmony is one of the biggest challenges in modern physics. To understand the problem, it helps to look at what each theory explains. Quantum mechanics is like a set of rules for the smallest building blocks of the universe. Electrons, photons, and other tiny particles follow strange rules. They can exist in multiple states at once and only seem to settle on one when measured. These rules might sound odd, but they are backed by experiments. For instance, the double-slit experiment shows how particles like electrons behave as waves and particles at the same time. This kind of behavior is fundamental to the quantum world. General relativity focuses on how massive objects like planets and black holes interact. It explains gravity as the result of how mass warps space and time. Picture a trampoline with a heavy ball in the center. If you roll a smaller ball across the surface, it curves around the heavy ball because the fabric is bent. Space works in a similar way, but in 3 dimensions. The presence of mass bends space and time, creating what we perceive as gravity. General relativity has been tested in many ways, from predicting the bending of light around the sun to the detection of gravitational waves. The conflict between the two theories becomes clear when you try to use them together. General relativity assumes that space and time are smooth. Quantum mechanics, however, shows that at very small scales, space and time behave unpredictably. Tiny fluctuations occur everywhere, making the smooth fabric of general relativity break down. This is most apparent in extreme environments, like the center of black holes or the moment of the Big Bang. In these situations, you need both quantum mechanics and general relativity to work together, but they don't. A good way to think about this conflict is to imagine 2 rules for games that overlap. One game is played on a smooth board, while the other is played with dice that change size randomly. If you try to combine these 2 games, the rules start to contradict each other. The smooth board doesn't account for the randomness of the dice, and the dice can't follow the smooth rules of the board. This is what happens when physicists try to apply quantum mechanics to the curved space of general relativity. Attempts to unify these theories have led to new ideas. One of the most well-known is string theory. String theory suggests that the smallest particles are not points but tiny vibrating strings. These strings exist in more dimensions than we can see, up to 10 or more. The vibrations of the strings determine the properties of particles, like their mass or charge. String theory has the potential to combine the rules of quantum mechanics with general relativity. It does this by changing how space and time work at small scales, smoothing out the conflicts. Another idea is loop quantum gravity. Instead of viewing space as continuous, loop quantum gravity treats it as made of tiny chunks or loops. These loops are incredibly small, much smaller than anything we can currently measure. By treating space in this way, loop quantum gravity tries to merge the smooth curves of general relativity with the unpredictable nature of quantum mechanics. This approach has produced interesting results, but it has not been tested directly. One challenge in unifying these theories is the lack of experimental evidence. The scales at which quantum gravity becomes important are far beyond what we can currently observe. For instance, black holes and the Big Bang are places where quantum gravity likely plays a role, but they are difficult to study in detail. To make progress, physicists need either new experiments or new ways to test these ideas indirectly. Despite these challenges, the search for a unified theory continues. One reason is that such a theory could solve many unanswered questions. For example, we don't fully understand what happens inside a black hole. General relativity predicts a singularity where gravity becomes infinite. Quantum mechanics suggests that singularities might not exist, but it doesn't explain what replaces them. A unified theory could provide answers. Another question is about the origin of the universe. The Big Bang is often described as a moment when space and time began. However, the physics of the Big Bang is incomplete. General relativity works well up to a point, but it breaks down at the very beginning. Quantum mechanics might explain what happened, but only if it can work with general relativity. A unified theory could provide a complete picture. The search for this unification also touches on philosophical questions. What is space? What is time? Are they fundamental, or do they emerge from something deeper? General relativity treats space and time as interconnected, while quantum mechanics suggests they might not be fundamental. A unified theory could change how we think about these basic concepts. While the goal of unification remains elusive, progress is being made. Theoretical work continues to refine ideas like string theory and loop quantum gravity. At the same time, experiments are pushing the boundaries of what we can observe. For example, the detection of gravitational waves has opened a new way to study extreme environments. Particle accelerators like the Large Hadron Collider are probing the smallest scales of matter. These efforts may eventually provide clues about how to unify quantum mechanics and general relativity. In the end, the question of unification is not just about solving a puzzle, it's about understanding the universe at its most fundamental level. The two theories we have now are incredibly powerful, but they are incomplete. Finding a way to bring them together could lead to new insights about everything from the smallest particles to the largest structures in the cosmos. It is a challenge that will take time, but the potential rewards are enormous. By addressing this mystery, we take another step toward understanding the nature of reality itself. Fundamental constants are numbers in nature that do not change. These constants, like the speed of light or the gravitational constant, shape how the universe behaves. Without them, the universe would be unrecognizable. For instance, the speed of light, approximately 299,792 kilometers per second, determines how quickly information and energy can travel through space. Similarly, the gravitational constant dictates the strength of gravity. Scientists know these numbers are vital, but they don't know why they have the specific values they do. The fundamental constants seem finely tuned. If you change their values even slightly, the universe might not support life. Take the strength of the electromagnetic force. This force holds atoms together. If it were a bit stronger, electrons would bind too tightly to nuclei, preventing the chemistry necessary for life. If it were weaker, atoms might not form at all. This precision is often called the fine-tuning problem. It raises an important question. Why do these constants have these values? One idea is that these constants are fixed features of our universe. They may simply be facts of nature, much like the existence of stars or planets. In this view, there's no deeper reason for their values, they just are. This idea can be unsatisfying because it doesn't explain the why, but it aligns with how science sometimes works. There are patterns and facts in nature that we observe without knowing their underlying cause. Another explanation involves the concept of a multiverse. The multiverse theory suggests our universe is just one of countless others. Each of these universes might have different constants. In this scenario, the values of the constants in our universe are not special. They're just one set among many. We happen to live in a universe with constants that allow for stars, planets, and life, because without them, we wouldn't be here to ask the question. This idea is called the anthropic principle. While it doesn't explain why these constants have their particular values, it suggests that our universe's constants might not be unique. The multiverse idea can be hard to grasp because we can't directly observe other universes. Imagine rolling a die. If you roll a 6, it might seem special, but if you roll it many times, you'll eventually get a 6 by chance. The multiverse theory applies similar reasoning. With enough universes, one will have the right constants for life, just as rolling a die enough times will produce a 6. Another possibility is that the values of the constants are determined by deeper physical laws we don't yet understand. Scientists have discovered connections between certain constants, suggesting they might not be as random as they seem. For example, the strength of the electromagnetic force and the mass of particles like protons are related in ways that hint at an underlying structure. If we understood this structure, we might discover why the constants have the values they do. This approach often involves unifying different areas of physics, such as quantum mechanics and gravity, into a single framework. The quest for such a theory, sometimes called a theory of everything, is ongoing. Some physicists explore whether these constants could vary over time. If they do, it might provide clues about how they came to have their current values. However, so far, experiments have found no evidence of significant variation. The constants appear to be just that, constant. Their stability over billions of years adds to their mystery. Why should these values stay fixed while the universe changes in so many other ways? Imagine building a house where every beam and nail has to fit perfectly, or the structure collapses. The fundamental constants are like those beams and nails. They hold the universe together. If you changed one value slightly, the whole structure could fall apart. For example, if the gravitational constant were much stronger, stars might burn out too quickly to support life. If it were weaker, they might not form at all. This delicate balance is why some people find it hard to believe these values are random. One analogy that helps illustrate the fine-tuning problem involves tuning a radio. If you move the dial even a little, you lose the station. The universe's constants seem similarly fine-tuned. It's as if someone set the dials just right to create a universe where life is possible. But who or what set the dials? Was it chance, necessity, or something else entirely? These questions make the study of fundamental constants one of the deepest puzzles in science. Some people see fine-tuning as evidence of a designer or creator. They argue that the precise values of the constants are unlikely to arise by chance. Others point out that invoking a designer raises its own questions. For example, who designed the designer? While this perspective doesn't offer a scientific explanation, it highlights how deeply this question resonates with people from all backgrounds. The search for answers continues in many ways. Physicists run experiments to test theories that might explain the constants. They also use powerful computers to simulate different scenarios and explore what happens when the constants change. These efforts haven't provided a final answer yet, but they have revealed surprising patterns. For example, some theories suggest that certain constants are related through symmetry principles. Symmetry is a concept where certain changes leave a system looking the same. It's like rotating a snowflake. It looks the same even after you turn it slightly. These symmetries might hold the key to understanding why the constants have their values. Another way scientists explore this mystery is by studying the early universe. The conditions right after the Big Bang were extreme, and the laws of physics may have behaved differently. By examining how the universe evolved, researchers hope to learn whether the constants emerged naturally from these early conditions. For example, some theories propose that constants like the speed of light or the gravitational constant could have been determined during the universe's first moments. This question doesn't just matter to physicists. Understanding why the constants are what they are could reveal whether life is common or rare in the universe. If the constants are random, it might mean that most universes are inhospitable. If they follow deeper rules, it could suggest that life is more likely to arise elsewhere. Either way, the implications are profound. The fundamental constants are like the rules of a game, and we're still figuring out why the game works the way it does. These constants define how particles interact, how stars shine, and how life exists. They are the foundation of everything we know, yet their origin remains a mystery. By studying them, we hope to uncover new insights about the universe and our place in it. Scientists may not have all the answers yet, but every step forward deepens our understanding and brings us closer to solving this puzzle. Quantum entanglement is a phenomenon in physics that describes a special connection between particles. When particles are entangled, the state of one is directly related to the state of the other, even if they are separated by vast distances. This connection happens instantly, which challenges our understanding of how information moves in the universe. To understand this better, it helps to break it down step by step and use some simple examples to clarify what is going on. Imagine you have two coins and you prepare them in a unique way. When you toss them, they will always land on the same side, either both heads or both tails, no matter how far apart they are. If you toss one coin in your living room and someone else tosses the other on another continent, the result will still match. This strange link doesn't depend on how far apart the coins are or how much time has passed since they were prepared together. It's as if the coins are connected in a way we can't easily see. In the quantum world, things like particles of light called photons or tiny pieces of matter like electrons can be entangled in a similar way. The difference is that instead of heads or tails, the particles have properties like spin or polarization, which are more complex than flipping a coin, but follow the same basic principle. These properties remain connected across distance, and measuring one particle tells you what the other particle's property is immediately. This might sound simple at first, but there's a twist that makes entanglement so strange. When you measure a property of a quantum particle, such as its spin, you don't see it as a fixed value beforehand. Instead, quantum mechanics says the property exists in a combination of possibilities, often called a superposition. Only when you measure the particle does it take on a specific value, like spin up or spin down. Before that, it's as if it's both at the same time. With entangled particles, the measurement of one forces the other to also settle into a specific state instantly, no matter how far apart they are. Let's go back to the coin example to illustrate this further. Imagine you and a friend have two coins that are entangled. You are in New York and your friend is in Tokyo. You flip your coin and it lands on heads. At that exact moment, without flipping the second coin, your friend looks at theirs and sees that it has also landed on heads. It's as if the two coins know what the other is doing. But unlike real coins, which can have a hidden cause determining their outcomes, quantum particles don't seem to have this hidden mechanism. They only decide on their states when someone measures them. This strange behavior has been tested many times in experiments. One famous type of test is called a Bell test, named after physicist John Bell, who showed how to check if particles are really behaving in this unusual way or if there is a hidden explanation. These experiments involve creating entangled pairs of particles and then measuring their properties under controlled conditions. The results consistently show that the particles are connected in a way that can't be explained by any hidden communication between them. This challenges our usual ideas of cause and effect and suggests that the rules of quantum mechanics are different from the rules we use to understand the everyday world. Another important detail about quantum entanglement is that it doesn't involve sending information faster than light. This is a common misunderstanding. While the measurement of one particle affects the other instantly, you can't use this to send a message or communicate faster than light. That's because the outcome of the measurement is random. You can't control what you see when you measure one particle, so you can't encode information in it. This means entanglement doesn't break Einstein's theory of relativity, which says nothing can travel faster than the speed of light. Quantum entanglement isn't just a curious phenomenon. It has practical applications and is at the heart of technologies that scientists are developing. One example is quantum computing, where entanglement is used to process information in new and powerful ways. Regular computers process bits of information as zeros and ones, like light switches that are either off or on. Quantum computers use quantum bits, or qubits, which can be 0, 1, or a combination of both, thanks to superposition. When qubits are entangled, they work together in ways that allow the computer to solve certain problems much faster than ordinary computers. Another area where entanglement is useful is quantum cryptography. This involves creating secure communication systems that use entangled particles to detect if someone is trying to eavesdrop on a message. If an eavesdropper tries to measure the particles, the entanglement is disrupted, and the people communicating can tell that their message is no longer secure. This could lead to more secure ways of protecting sensitive information in the future. Quantum entanglement also raises deep philosophical questions about the nature of reality. One question is whether the particles are truly connected in some fundamental way, or if the universe itself behaves differently than we imagine. Einstein was famously uncomfortable with entanglement and called it spooky action at a distance. He believed there must be a better explanation, such as hidden variables that we don't yet understand. However, experiments have repeatedly shown that hidden variables don't seem to work as an explanation, leaving entanglement as a central mystery of physics. Despite these insights, there are still many unanswered questions about entanglement. Scientists don't fully understand why it exists or how it fits into a complete picture of the universe. It's also unclear how entanglement might connect to other areas of physics, such as gravity or the theory of relativity. Some researchers think studying entanglement could help solve these bigger puzzles, like finding a theory that unifies quantum mechanics and general relativity. To sum up, quantum entanglement is a fascinating and mysterious part of nature. It shows how particles can remain connected in ways that defy our everyday experience. It has been proven through experiments and is being used in cutting-edge technologies like quantum computing and cryptography. Yet it also challenges our understanding of reality and raises questions about how the universe works on its most fundamental level. As scientists continue to explore entanglement, they may uncover even deeper truths about the quantum world and its connection to the universe we live in. Aging is one of the most universal and inevitable processes in life. It affects every living organism, but what causes it is a complex puzzle that scientists are still piecing together. At its simplest, aging refers to the gradual changes that occur in the body over time, leading to decreased function and an increased risk of disease or death. While this definition seems straightforward, the underlying causes of aging are anything but simple. To understand aging, it helps to think of the body as a highly sophisticated machine. Like any machine, it starts in pristine condition. Over time, though, wear and tear set in, parts degrade, and processes become less efficient. In humans, this wear and tear happens at the cellular level, where tiny structures called cells are responsible for every function in the body. These cells form tissues, which then make up organs like the heart, liver, and skin. When cells function well, the body stays healthy. But as cells age, problems arise. One of the key causes of aging is damage to DNA, the blueprint for all life. DNA sits inside almost every cell in the body, carrying the instructions that tell cells how to grow, repair themselves, and function. Every day, DNA faces assaults from various sources. Some of this damage comes from outside the body, such as ultraviolet light from the sun or harmful chemicals in the air. Other damage happens naturally, as a byproduct of processes that occur inside cells. For instance, when cells use oxygen to produce energy, they generate waste products called free radicals. These free radicals can interact with and harm DNA, proteins, and other important molecules in cells. Over time, the accumulation of this damage disrupts normal cell function. Cells have mechanisms to repair DNA, and they do a remarkable job of fixing most problems. But they aren't perfect. Some damage slips through, and over decades, this unrepairable damage builds up. As cells become less effective at repairing themselves, they stop working properly or die. In some cases, damaged cells continue to function but enter a state called senescence. Senescent cells don't divide or contribute to the body's needs. Instead, they can release signals that trigger inflammation and harm nearby healthy cells. The accumulation of these zombie-like cells is another factor in aging. Another cause of aging involves telomeres, which are structures found at the ends of chromosomes, the long strands of DNA in our cells. Telomeres are often compared to the plastic tips on shoelaces because they protect chromosomes from unraveling or sticking to each other. Each time a cell divides, its telomeres become shorter. Eventually, they become so short that the cell can no longer divide. When this happens, the cell either dies or becomes senescent. Shortened telomeres act like a clock, limiting the number of times a cell can divide and contributing to aging. The body's ability to maintain itself also depends on its systems for removing waste. Cells produce waste materials as part of their normal activities, and they have mechanisms to dispose of this waste. But with age, these systems become less efficient. Misfolded proteins, for example, can accumulate and form clumps inside or outside cells. These clumps interfere with cell function and are linked to age-related diseases like Alzheimer's. Similarly, damaged or worn-out parts of cells can pile up, leading to dysfunction and stress. Aging also involves changes in how genes are expressed. Genes can be thought of as switches that turn on or off specific instructions for the cell. Over time, some of these switches get stuck in the wrong position. This can cause cells to produce too much or too little of certain proteins, disrupting their balance. These changes are influenced by the environment, lifestyle, and even experiences. The study of how environmental factors affect gene expression is called epigenetics, and it has become an important area of research in aging. Another factor is the immune system, which plays a critical role in protecting the body from infections, removing harmful cells, and repairing tissues. As we age, the immune system becomes less effective. It may fail to detect and destroy harmful cells, such as those that could turn into cancer. At the same time, the immune system may become overactive, leading to chronic inflammation. This inflammation, often called inflammaging, has been linked to many age-related diseases, including heart disease, diabetes, and arthritis. The decline in hormones is another hallmark of aging. Hormones are chemical messengers that regulate almost every function in the body, from growth to metabolism to mood. Levels of certain hormones, like estrogen and testosterone, drop with age. These changes can affect muscle mass, bone density, and even the way the body stores fat. For example, the loss of testosterone in men and estrogen in women contributes to osteoporosis, a condition where bones become weak and prone to breaking. One way to think about aging is to imagine a car that has been driven for decades. The engine no longer runs as smoothly, the paint begins to peel, and rust appears in the corners. You can slow down the wear and tear with proper maintenance, regular oil changes, tire rotations, and washing, but you can't stop it entirely. Similarly, good nutrition, exercise, and avoiding harmful habits like smoking can help keep the body functioning better for longer. However, the underlying processes of aging will still continue. Scientists have identified many causes of aging, but they still don't fully understand why it happens or how to prevent it. There are theories that suggest aging is programmed into our biology, like a timer that counts down the years and eventually runs out. Other theories suggest that aging is a byproduct of living, an unavoidable consequence of the damage that accumulates as we go through life. Most experts believe it's a combination of both. Some researchers are exploring ways to slow down or even reverse aspects of aging. One approach focuses on targeting senescent cells. By removing these harmful cells, scientists have extended the lifespan of mice in experiments and improved their health. Another area of research involves telomeres. Scientists are looking at ways to extend telomeres or protect them from shortening, which could potentially delay the aging process. Advances in gene editing and regenerative medicine also hold promise for addressing some of the underlying causes of aging. While these discoveries are exciting, it's important to remember that aging is deeply tied to the nature of life itself. The processes that cause aging also make growth, reproduction, and healing possible. Even though we may never fully stop aging, understanding its causes helps us improve health and extend the years of life spent in good health. By unraveling the mysteries of aging, we can aim for a future where growing older is less about decline and more about living well. Consciousness disorders like Alzheimer's disease are some of the most devastating conditions that affect the human mind. They rob individuals of their memories, their sense of self, and their ability to connect with others. Despite decades of research, we still don't fully understand why these disorders occur. However, scientists have uncovered several key factors that help us piece together the roots of these conditions. Alzheimer's disease is the most common cause of dementia, a term used to describe a decline in mental ability severe enough to interfere with daily life. Alzheimer's is characterized by progressive memory loss, difficulty in problem solving, and changes in behavior. At its core, it is a disease that affects the brain, specifically how brain cells communicate, work, and survive. Understanding its roots involves exploring a combination of biological, genetic, and environmental factors. One of the hallmarks of Alzheimer's is the buildup of abnormal proteins in the brain. Imagine a city's streets getting clogged with trash over time, making it impossible for cars to move. Similarly, the brain of someone with Alzheimer's gets clogged with two main types of protein, beta amyloid and tau. Beta amyloid proteins form sticky plaques that accumulate between brain cells. Tau proteins, on the other hand, form tangles inside the cells. These plaques and tangles disrupt the way brain cells communicate with each other. Over time, this disruption leads to the death of brain cells, or neurons, causing the brain to shrink and lose its ability to function. To understand why these proteins build up, researchers look at both genetic and environmental factors. Some people are more likely to develop Alzheimer's because of their genes. For example, a gene called APOE has been strongly linked to the disease. Everyone inherits 2 copies of the APOE gene, one from each parent. The type of APOE gene you inherit can influence your risk. For instance, the APOE E4 version increases the likelihood of developing Alzheimer's, although it doesn't guarantee it. Other rare genetic mutations, found in families with a strong history of Alzheimer's, can almost certainly lead to early onset forms of the disease. However, most cases of Alzheimer's occur in older people without these rare mutations. Genes, while important, are not the whole story. Many people with riskier genes never develop Alzheimer's, while others with no family history of the disease do. This suggests that lifestyle and environmental factors play a role. Scientists are particularly interested in how cardiovascular health affects the brain. The brain relies on a constant supply of oxygen and nutrients delivered by the blood. When blood flow to the brain is reduced, due to conditions like high blood pressure, heart disease, or diabetes, the risk of Alzheimer's increases. This link between heart and brain health has led to the idea that what's good for the heart is also good for the brain. Another area of interest is inflammation. When the body senses damage or infection, it triggers an immune response to protect itself. This response, called inflammation, is usually helpful in the short term, but chronic inflammation can harm the body, including the brain. In Alzheimer's, inflammation may be a double-edged sword. Some studies suggest that the immune system tries to clear away plaques and tangles, but in doing so, it can damage healthy brain cells. Over time, this constant state of inflammation might make the disease worse. Lifestyle choices also play a significant role in Alzheimer's risk. For instance, physical activity has been shown to reduce the likelihood of developing the disease. Exercise improves blood flow to the brain, reduces inflammation, and promotes the growth of new brain cells. On the other hand, a sedentary lifestyle, combined with poor diet, can increase the risk. Obesity, high cholesterol, and a lack of regular exercise are all linked to worse brain health over time. Sleep is another factor that researchers are investigating. The brain doesn't just rest during sleep, it also cleans itself. During deep sleep, the brain flushes out waste products, including beta amyloid. Chronic sleep problems, like insomnia or sleep apnea, might interfere with this cleaning process, leading to a buildup of harmful proteins. This could explain why poor sleep is linked to an increased risk of Alzheimer's. Mental and social activity also seem to protect against Alzheimer's. Engaging the brain through learning, problem-solving, or social interaction helps to build what scientists call cognitive reserve. Cognitive reserve is like a backup system for the brain. Even if Alzheimer's starts to cause damage, people with higher cognitive reserve can often function better for longer. Activities like reading, playing games, or staying socially connected appear to strengthen this reserve. While all these factors, genetic, biological, lifestyle, and environmental, contribute to Alzheimer's, they don't act in isolation. Instead, they interact in complex ways. For example, someone with a high genetic risk for Alzheimer's might delay or even prevent the disease by staying physically active, eating a healthy diet, and maintaining strong social connections. Conversely, someone with no genetic predisposition might still develop the disease if they experience poor cardiovascular health or chronic inflammation. Understanding the roots of Alzheimer's isn't just about identifying risk factors. It's also about figuring out what goes wrong in the brain at a molecular level. Scientists are still debating the exact sequence of events that leads to Alzheimer's. Some believe that beta amyloid plaques are the primary cause, setting off a cascade of problems that eventually lead to tau tangles and cell death. Others argue that tau tangles are the main culprit, with plaques playing a secondary role. There's even a growing body of evidence that suggests a third possibility, that infections or imbalances in the brain's microbiome might trigger the disease. One interesting theory is that beta amyloid might be part of the brain's defense against infection. If this is true, the plaques seen in Alzheimer's could be the result of the brain overreacting to a threat. This idea is still being tested, but it could explain why some people develop Alzheimer's while others with similar risk factors do not. Despite the many advances in understanding Alzheimer's, much remains unknown. Why do some people with plaques and tangles never show symptoms? Why does the disease progress so much faster in some than in others? And most importantly, how can we stop or reverse the disease? These are the questions that drive researchers today. Alzheimer's disease is a complex condition with no single cause. Its roots lie in the interplay between genes, biology, and the environment. While we have made great strides in understanding the disease, there is still a long way to go. By continuing to explore these roots, scientists hope to unlock new treatments and one day find a way to prevent this devastating condition altogether. A placebo is a substance or treatment with no active therapeutic ingredients, yet it can sometimes lead to noticeable improvements in a person's condition. This effect is called the placebo effect, and it has puzzled scientists and physicians for decades. At first glance, it might seem strange that something as simple as a sugar pill or a saline injection could have any impact on health. To understand how this works, it helps to explore the relationship between the mind and body, the role of expectations, and the underlying mechanisms that might explain why placebos sometimes work. Imagine a person with chronic pain participating in a clinical trial for a new pain medication. Without knowing, they are given a placebo, a pill containing no actual pain-relieving ingredients. To their surprise, they start feeling better. They report less pain and even greater mobility. How is this possible? Part of the answer lies in their belief that the pill is real medicine. When someone believes they are receiving an effective treatment, their brain can respond as though the treatment is actually working. Expectations play a crucial role in this process. If a person expects to feel better, their brain might release natural chemicals, such as endorphins, that mimic the effects of real medication. Endorphins are the body's own painkillers. They act on the same pathways in the brain as drugs like morphine or codeine. This is why someone who believes they have taken a pain reliever may genuinely experience less pain, even though they haven't ingested any active drug. The expectation of relief can be enough to trigger a biological response. The environment and context in which a placebo is given can also influence its effectiveness. Consider the way medications are typically administered. A doctor's confidence, a reassuring tone, or even the way a pill looks can shape a patient's expectations. If a patient sees a doctor in a white coat, hears comforting words, and receives a pill that looks professional, these cues reinforce the belief that the treatment will work. This is sometimes called the ritual of treatment. It highlights how much the process of receiving care can matter, not just the treatment itself. Placebos can also work differently depending on the condition being treated. For example, they tend to be most effective for symptoms that involve perception, like pain, fatigue, or nausea. These are conditions where the brain plays a key role in interpreting and managing the experience. In cases like these, a placebo can alter the way the brain processes signals from the body. Pain, for instance, isn't just a physical sensation. It's also shaped by emotions, attention, and prior experiences. By influencing these factors, a placebo can reduce the perception of pain, even if the underlying cause remains unchanged. Take another example. In studies on depression, some patients given placebos report feeling less sad or more energetic. Again, this might be because of the expectation of improvement, but it could also be due to changes in brain activity. Research has shown that certain areas of the brain, such as the prefrontal cortex, can become more active when a person believes they are being treated for depression. This increased activity may help regulate mood and improve emotional resilience, even in the absence of an active drug. The power of the placebo effect highlights how much of medicine depends on the mind-body connection. This connection can work in surprising ways. In some cases, a placebo can even trigger side effects. This is called the nocebo effect. If a person is told that a pill might cause headaches, they might develop headaches, even if the pill contains nothing but sugar. This shows how strongly expectations and beliefs can influence the body. It also demonstrates that the placebo effect is not always positive. It can sometimes make people feel worse. One fascinating aspect of the placebo effect is that it can work even when people know they are taking a placebo. In some studies, participants were told explicitly that their pills contained no active ingredients. Surprisingly, some of these participants still reported improvements in their symptoms. This suggests that the act of taking a pill or receiving a treatment, even when the magic is removed, can still engage the brain in a way that promotes healing or relief. It's as if the ritual itself has power, independent of deception. The placebo effect is not limited to pills or injections. It can occur with surgeries, physical therapies, and even devices. For example, some studies have shown that patients who undergo sham surgeries, where no real procedure is performed, sometimes report improvements in their symptoms. Similarly, people using fake acupuncture needles or deactivated devices often experience benefits if they believe the treatment is real. This reveals how deeply the brain's expectations can shape physical outcomes. Understanding the mechanisms behind the placebo effect can help improve healthcare. If doctors can harness the positive aspects of this effect, they might be able to enhance the overall effectiveness of treatments. For instance, the way a doctor interacts with a patient, showing empathy, building trust, and offering reassurance, might amplify the impact of real medications by tapping into the same psychological and biological pathways that drive the placebo effect. This doesn't mean replacing real treatments with placebos. Instead, it means acknowledging the importance of the mind in healing and using that knowledge to improve patient care. Even though the placebo effect is well documented, it raises some ethical questions. In clinical trials, placebos are often used to test the effectiveness of new treatments. This is done by comparing a group that receives the treatment to a group that receives a placebo. But when it comes to actual medical practice, using a placebo can be controversial. Some people argue that prescribing a placebo without telling the patient is deceptive, even if it might help them feel better. Others believe that the benefits of the placebo effect justify its use in certain situations. This ethical debate underscores how complex the relationship between mind, body, and medicine can be. Despite years of research, there is still much to learn about how placebos work. Scientists continue to explore the biological mechanisms involved, such as changes in brain activity, hormone release, and immune system function. They also study the psychological aspects, like how expectations, conditioning, and trust influence the effect. By understanding these factors, researchers hope to unlock new ways to use the placebo effect to complement traditional medicine. Ultimately, the placebo effect reminds us of the remarkable power of the mind. It shows that healing is not just a mechanical process, but also a deeply personal and psychological one. Whether through the belief in a treatment, the rituals of care, or the complex interactions between brain and body, the placebo effect is a window into how interconnected our mental and physical health truly are. It challenges us to think differently about medicine and to consider the ways in which hope, belief, and human connection contribute to the process of healing. Deep beneath the surface of the Earth lies a region we have never directly observed, the core. It sits about 800 miles below our feet and stretches another 2,200 miles to the planet's center. Despite being so far removed from human reach, we have managed to piece together a picture of what it might look like and how it behaves. This understanding comes from careful studies of seismic waves, laboratory experiments, and our knowledge of physics and chemistry. Still, the core remains one of the most mysterious places on Earth. The Earth's core consists of two parts, the outer core and the inner core. These layers have different properties and compositions, which we know because of the way seismic waves from earthquakes travel through them. Seismic waves behave differently depending on the material they pass through. Some waves move faster through solid rock, while others slow down or stop entirely when they encounter liquid. Scientists use these changes in speed and direction to map the structure deep inside the Earth. The outer core is a liquid layer made mostly of iron and nickel. This layer begins about 1,800 miles below the surface and extends down to about 3,200 miles. It is extremely hot, with temperatures ranging from about 4,500 to 6,000 degrees Celsius. That's hotter than the surface of the sun. The intense heat is enough to keep the metals in this layer in a molten state, meaning they flow like a thick, hot soup. This movement of liquid iron in the outer core is incredibly important for life on Earth. It creates our planet's magnetic field. The flowing metal acts like a giant dynamo, generating electricity and magnetic forces as it moves. This magnetic field extends out into space and shields us from harmful solar radiation. Without it, the solar wind, streams of charged particles from the sun, would strip away Earth's atmosphere, leaving it barren like Mars. The fact that this life-protecting shield comes from deep inside the Earth is a fascinating example of how connected our planet's systems are. Deeper still lies the inner core. Unlike the outer core, the inner core is solid. It is mostly made of iron, with smaller amounts of nickel and other elements, such as silicon or sulfur. The inner core begins where the liquid outer core ends, at a depth of about 3,200 miles, and extends to the Earth's center, around 4,000 miles down. Even though it is solid, the inner core is just as hot as the outer core, with temperatures estimated to reach around 6,000 degrees Celsius. That's nearly as hot as the surface of the sun. You might wonder why the inner core is solid while the outer core is liquid, even though both are made of similar materials and the inner core is even hotter. The answer lies in pressure. As you go deeper into the Earth, the pressure increases because of the weight of all the rock and metal above. At the center of the Earth, the pressure is about 3.6 million times greater than at the surface. This immense pressure forces the atoms in the inner core so tightly together that they can't move freely, which keeps the material solid despite the intense heat. The inner core isn't a single, uniform piece of metal. Evidence suggests it has layers of its own, with a solid inner region surrounded by an outer region that might have slightly different properties. Some researchers also think the inner core is slowly growing. As the Earth cools, more of the liquid iron from the outer core solidifies onto the inner core, adding to its size over millions of years. This process releases heat, which contributes to the movement of the liquid outer core and keeps the dynamo running. Despite all this knowledge, many mysteries about the core remain. For example, scientists debate the exact composition of the inner and outer core. We know they are mostly iron and nickel, but small amounts of lighter elements like silicon, sulfur, or oxygen could also be present. These lighter elements might explain why the core is slightly less dense than pure iron. Figuring out the exact mix is difficult because we can't sample the core directly. Instead, researchers rely on indirect clues, such as how seismic waves travel through the Earth and how metals behave under high pressure in laboratory experiments. Another mystery involves the inner core's rotation. Some evidence suggests it rotates slightly faster or slower than the rest of the Earth. This superrotation, as scientists call it, is thought to be caused by the interactions between the core and the magnetic field it generates. However, the details of how this works are not fully understood. Similarly, the way the outer core's liquid flows to create the magnetic field is a topic of ongoing research. While we have models that explain the general process, the exact mechanisms are complex and not completely clear. Studying the core is challenging because of its inaccessibility. The deepest hole ever drilled into the Earth, the Kola Superdeep borehole in Russia, reached a depth of about 7.5 miles, just a fraction of the distance to the core. To learn about what's down there, scientists rely on seismic data, which comes from studying how earthquake waves travel through the Earth. These waves give us a rough map of the core's structure. Researchers also use computer models and experiments where they subject materials like iron and nickel to extreme heat and pressure to simulate core conditions. Understanding the core isn't just an academic exercise. It has real-world implications for life on Earth and the study of other planets. For example, learning about the core helps us understand the magnetic field, which protects life from harmful solar radiation. It also helps us study plate tectonics and volcanic activity, both of which are influenced by the heat flowing from the core to the mantle and crust. By studying Earth's core, we can also make comparisons to other planets. Mars, for instance, no longer has a magnetic field, possibly because its core cooled and solidified. Understanding what happened to Mars can give us insights into the long-term future of Earth. The Earth's core is a hidden world, incredibly far from human reach, yet vital to life on the surface. It is a place of extreme heat and pressure, where liquid metals flow to create a protective magnetic field, and solid iron rests at the center of it all. Despite the challenges of studying it, scientists continue to make progress in understanding this mysterious region. Each discovery brings us closer to answering the many questions that remain, but the core still holds many secrets waiting to be uncovered. The deep ocean is one of the most mysterious and least explored parts of our planet. Despite covering over 70% of Earth's surface, much of the ocean remains unknown to us, especially the areas far below the surface. These depths hold an extraordinary variety of ecosystems, geological features, and life forms, some of which seem almost otherworldly. Scientists estimate that over 80% of the ocean is unmapped and unexplored, leaving a vast frontier beneath the waves. Understanding what lies in these deep waters means looking at everything from the creatures that live there to the geology and chemistry of the seafloor itself. Most of the deep ocean exists in darkness. Sunlight penetrates only the uppermost layer, known as the epipelagic or sunlight zone. Below that, the light fades quickly as you enter the mesopelagic or twilight zone. Deeper still is the bathypelagic zone, often called the midnight zone, where no sunlight reaches at all. The deeper you go, the greater the pressure becomes. At the deepest points in the ocean, the pressure is so intense it would crush most human-made objects. This environment is cold, with temperatures just above freezing, and yet life thrives here in ways that continue to astonish researchers. One of the most intriguing aspects of the deep ocean is the life it supports. In the absence of sunlight, many organisms rely on other energy sources, such as chemical reactions. At hydrothermal vents, for example, seawater interacts with the Earth's crust to produce heat and chemicals like hydrogen sulfide. Some bacteria use these chemicals to create energy through a process called chemosynthesis. These bacteria form the base of an entire ecosystem, supporting creatures like giant tube worms, crabs, and fish. These organisms are unlike anything you might find in shallower waters. Tube worms, for instance, can grow several feet long and lack mouths or digestive systems. Instead, they have a symbiotic relationship with bacteria inside their bodies that provide them with nutrients. Beyond hydrothermal vents, other parts of the deep ocean are equally fascinating. Cold seeps are areas where methane and other gases seep out of the seafloor. Like hydrothermal vents, these sites support unique ecosystems built around chemosynthesis. In addition to these biological wonders, there are creatures that seem almost alien. The anglerfish, with its bioluminescent lure, is a classic example. It uses a glowing appendage on its head to attract prey in the pitch-black darkness. The gulper eel, with its enormous mouth and tiny body, can swallow prey much larger than itself. Bioluminescence is a common adaptation in the deep ocean. Many creatures produce their own light through chemical reactions, which helps them communicate, attract mates, or confuse predators. The geology of the deep ocean is equally remarkable. The seafloor is not a flat, featureless plain, but a landscape of mountains, valleys, and trenches. Underwater mountain ranges, like the Mid-Atlantic Ridge, stretch for thousands of miles, forming the longest continuous mountain chain on Earth. These ridges are created by tectonic plates pulling apart, allowing magma to rise and create new crust. Subduction zones, where one plate slides beneath another, give rise to deep ocean trenches. The Mariana Trench in the Pacific Ocean is the deepest known point, plunging nearly 7 miles below the surface. Exploring these trenches is a daunting task, as the extreme pressure makes it difficult to send equipment or people down safely. The deep ocean also contains vast reserves of resources. Manganese nodules, which are rich in valuable metals, litter some areas of the seafloor. These nodules could be used in electronics and other industries, but mining them raises ethical and environmental questions. The ocean also holds an enormous amount of methane in the form of gas hydrates, a potential energy source that remains largely untapped. At the same time, the deep ocean acts as a massive carbon sink, absorbing carbon dioxide from the atmosphere and playing a critical role in regulating Earth's climate. Despite the challenges of exploring the deep ocean, technology has allowed us to learn more in recent decades. Remotely operated vehicles, or ROVs, have been essential for studying these depths. These robotic devices can withstand extreme pressures and transmit images and data back to researchers. Human-piloted submersibles, like the famous Alvin, have also made historic dives. However, these missions are costly and time-consuming, which limits how often they can be conducted. One of the greatest mysteries of the deep ocean is how much we still don't know. Scientists discover new species nearly every time they explore these depths, and some of these creatures challenge what we thought we knew about life. For example, in 2020, researchers found a species of jellyfish in the deep ocean that uses a unique form of propulsion unlike any seen before. Discoveries like this remind us of how little we understand about the organisms living far below the surface. The deep ocean also raises questions about the limits of life on Earth. Extremophiles, or organisms that live in extreme conditions, thrive in the deep ocean. Some live at temperatures near boiling at hydrothermal vents, while others endure crushing pressures in trenches. Studying these organisms helps us understand the potential for life in extreme environments elsewhere, such as on other planets or moons. If life can exist at the bottom of our oceans, it may also exist in the subsurface oceans of Jupiter's moon Europa or Saturn's moon Enceladus. Understanding the deep ocean is not just about curiosity. It has practical implications for science, technology, and conservation. The ocean influences global weather patterns and supports fisheries that millions of people rely on for food. It also holds clues to Earth's history, as sediment layers on the seafloor record changes in climate and geology over millions of years. Protecting these ecosystems is crucial, especially as human activities like deep-sea mining and climate change threaten their delicate balance. The deep ocean remains one of the final frontiers on Earth. Each discovery there expands our knowledge of life, geology, and the planet itself. Yet for all we have learned, the deep ocean reminds us of how much we still don't know. It challenges our assumptions and inspires us to keep exploring. Every journey into its depths is a step closer to understanding not just the ocean, but our place within the broader tapestry of life on Earth. Fast radio bursts, or FRBs, are one of the most intriguing puzzles in modern astronomy. These are incredibly brief but intense bursts of radio waves that last only a fraction of a second. Despite their short duration, they release an astonishing amount of energy, comparable to the amount of energy the sun emits over several days. Scientists first discovered FRBs in 2007 while reviewing data from a radio telescope, and since then, hundreds have been detected. They remain a source of fascination and speculation because their origins are still not fully understood. To understand why FRBs are so mysterious, it helps to think about what radio waves are and how they work. Radio waves are a type of electromagnetic radiation, similar to visible light, but with much longer wavelengths. They travel through space and can be detected using radio telescopes, which are giant antennas that pick up faint signals from the cosmos. The problem with FRBs is that they appear suddenly, without warning, and disappear just as quickly. This makes them hard to study and even harder to trace back to their source. What makes FRBs especially interesting is their enormous energy output. To put this into perspective, imagine a flashlight that shines as brightly as the sun. Now, imagine all of that energy concentrated into a single burst lasting just a millisecond. That's the kind of power we're talking about with FRBs. For such a brief event to produce so much energy, something truly extraordinary must be happening. Scientists have been trying to figure out where FRBs come from and what causes them. One of the biggest clues is that some FRBs come from very distant galaxies. When radio waves travel through space, they interact with the gas and dust they encounter along the way. This interaction causes a phenomenon called dispersion, where higher frequency radio waves arrive slightly earlier than lower frequency ones. By measuring this delay, scientists can estimate how far the FRB has traveled. In many cases, the distances are billions of light years, which means the source of the FRB is extremely far away. The extreme distances suggest that FRBs are not caused by ordinary events. Something powerful must be generating them. One possibility is that they come from neutron stars. Neutron stars are the dense remnants of massive stars that have exploded as supernovae. These stars are so compact that a single teaspoon of their material would weigh billions of tons. Some neutron stars have strong magnetic fields and are known as magnetars. Magnetars occasionally release massive bursts of energy when their magnetic fields twist or realign. This could create the kind of intense radio waves we see in FRBs. Another possible explanation is that FRBs come from black holes. When matter falls into a black hole, it can produce extreme bursts of energy. This process might generate radio waves strong enough to be detected as FRBs. Some researchers also think FRBs might be related to collisions between neutron stars or between a neutron star and a black hole. These collisions release immense amounts of energy and could potentially produce the radio waves we observe. Interestingly, some FRBs repeat. Most of the bursts detected so far have been one-time events, but a small number of them occur multiple times from the same location. This makes the mystery even deeper. If an FRB repeats, it rules out certain explanations, such as collisions, because those would be one-time events. Instead, it suggests a source that can produce bursts of energy repeatedly. Magnetars fit this description, but it's still not clear why some FRBs repeat and others don't. To make things even more puzzling, scientists have detected FRBs that seem to follow regular patterns. For example, one repeating FRB appears to burst every 16 days. This kind of regularity is unusual in astrophysical phenomena and has led to some creative theories. One idea is that the source of the FRB might be orbiting another object, such as a star or a black hole. As the source moves closer to or farther from Earth, its bursts might become more or less detectable, creating a periodic pattern. While these natural explanations are fascinating, some people have suggested more exotic possibilities. One idea is that FRBs could be signals from extraterrestrial civilizations. If an advanced alien species wanted to send a message across the galaxy, they might use powerful bursts of radio waves to do so. This idea is speculative, but it highlights just how little we understand about FRBs. It's worth noting that scientists generally favor natural explanations because they can be tested and verified, but the possibility of alien involvement keeps the discussion lively. Detecting and studying FRBs requires specialized equipment. Radio telescopes are the main tool used to capture these fleeting signals. Some of the most important discoveries about FRBs have come from instruments like the Parkes Observatory in Australia, the Arecibo Observatory in Puerto Rico, and the Canadian Hydrogen Intensity Mapping Experiment, CHIME. CHIME, in particular, has been revolutionary because it can observe large portions of the sky and detect multiple FRBs each day. This has dramatically increased the number of known FRBs and provided more data for scientists to analyze. One of the challenges in studying FRBs is pinpointing their exact locations. When a radio telescope detects an FRB, it provides a general direction but not a precise position. To locate the source more accurately, scientists need to use multiple telescopes spread across the globe. This technique, called very long baseline interferometry, allows researchers to triangulate the position of the FRB and trace it back to its home galaxy. Once the galaxy is identified, astronomers can study it using other types of telescopes, such as optical or X-ray telescopes, to learn more about the conditions that might produce an FRB. Despite these efforts, many questions remain unanswered. Are all FRBs caused by the same type of event, or are there multiple sources? Why do some FRBs repeat while others don't? What determines the intensity and frequency of the bursts? Answering these questions will require more observations and perhaps new technology. The mystery of FRBs is a reminder of how much we still have to learn about the universe. Even though we've made incredible advances in understanding the cosmos, phenomena like FRBs show us that there are still surprises waiting to be uncovered. Every new discovery about FRBs brings us a little closer to understanding them, but for now, they remain one of the most captivating enigmas in modern astronomy. Black holes are one of the most fascinating and mysterious objects in the universe. They are regions in space where gravity is so strong that nothing, not even light, can escape. This happens because so much mass is packed into a small space, creating a gravitational pull that overwhelms everything around it. To understand their nature, we need to look at how they form, what happens around them, and what makes them so unique. Black holes typically form when massive stars reach the end of their lives. Stars exist because of a balance between the inward pull of gravity and the outward pressure from nuclear fusion in their cores. Fusion is the process that powers stars, where hydrogen atoms combine to form helium and release energy. Over time, a star runs out of fuel, and when this happens, the outward pressure weakens. Gravity takes over, and the star collapses under its own weight. If the star is large enough, the collapse becomes so intense that it creates a black hole. To picture this, imagine compressing Earth into a ball just a few centimeters wide. The mass of Earth would stay the same, but its gravity would become unimaginably strong because it's concentrated in such a tiny space. This is similar to how black holes form. In fact, the defining feature of a black hole is something called the event horizon. This is the boundary around the black hole where gravity becomes so strong that escape is impossible. If you cross this boundary, there's no way to return. The event horizon is not a physical surface you can touch. It's more like an invisible border. Once you cross it, you are inevitably pulled toward the center of the black hole. Scientists call this center the singularity. The singularity is the point where gravity is thought to become infinite, and the laws of physics, as we know them, break down. What happens at the singularity is one of the biggest unsolved questions in science. The theories we currently use to describe the universe, like Einstein's general relativity, cannot handle the extreme conditions at this point. Black holes come in different sizes. Some are only a few times more massive than our Sun, while others, called supermassive black holes, are millions or even billions of times more massive. Supermassive black holes are often found at the centers of galaxies, including our own Milky Way. Scientists believe these black holes play a crucial role in shaping galaxies, but we don't fully understand how they form or why they grow so large. One of the most intriguing aspects of black holes is how they affect their surroundings. Although we can't see black holes directly, we can detect their presence through their interactions with nearby matter. For example, if a black hole is near a star, it can pull material away from the star. This material forms a disk as it spirals into the black hole. The disk heats up and emits radiation, which we can observe with telescopes. This is how scientists have identified many black holes. Another fascinating feature of black holes is their ability to bend light. This happens because of their strong gravitational pull, which warps the fabric of space. If light from a distant object passes near a black hole, it gets bent around it, creating a lensing effect. This effect can make objects behind the black hole appear distorted or magnified. Astronomers use this phenomenon to study distant galaxies and other celestial objects. Stephen Hawking, a famous physicist, proposed an idea that added another layer of mystery to black holes. He suggested that black holes are not entirely black. Instead, they slowly emit tiny amounts of radiation, now known as Hawking radiation. Over an incredibly long time, this radiation could cause a black hole to lose mass and eventually disappear. This idea challenged the earlier belief that nothing could escape a black hole. While Hawking radiation has not been observed directly, it has become an important concept in our understanding of black holes. Black holes also raise questions about the nature of information. According to the laws of physics, information about a system is never truly lost. For example, if you burn a piece of paper, the ash and smoke still contain the information about the paper's original state, even if it's no longer recognizable. However, when something falls into a black hole, it seems like that information is lost forever. This leads to what scientists call the information paradox. Resolving this paradox is one of the major challenges in modern physics. To make sense of these mysteries, scientists use tools like computer simulations and powerful telescopes. In recent years, we've made remarkable progress. In 2019, scientists captured the first ever image of a black hole. This was achieved using a network of telescopes around the world called the Event Horizon Telescope. The image showed the shadow of a black hole surrounded by a glowing ring of light. This groundbreaking achievement confirmed many of the predictions made by Einstein's theory of general relativity. Despite these advances, black holes remain deeply mysterious. For example, we don't fully understand what happens to space and time near the singularity. Some theories suggest that black holes could act as gateways to other parts of the universe, or even other universes. While these ideas are speculative, they show how black holes challenge our understanding of reality. Black holes also make us think about time in a new way. Close to a black hole, time slows down compared to places farther away. This effect, predicted by Einstein, has been tested and confirmed in less extreme environments. For example, clocks on satellites in orbit around Earth tick slightly faster than clocks on the ground because of the difference in gravity. Near a black hole, this effect becomes much stronger. If you were to watch someone fall into a black hole, it would appear to you as though they were moving slower and slower as they approached the event horizon. However, from their perspective, they would cross the event horizon without noticing anything unusual. The study of black holes is not just about understanding these objects themselves. It's also about testing the limits of our knowledge. Black holes push our theories of physics to their breaking points, revealing gaps that need to be filled. They force us to ask fundamental questions about space, time, and the nature of reality. In many ways, black holes are like cosmic laboratories. They allow us to explore ideas that would be impossible to test anywhere else. As we learn more about them, we may discover new principles that reshape our understanding of the universe. For now, they remain one of the most intriguing mysteries in science, challenging us to look deeper and think harder about the nature of existence. The idea of parallel universes, also called the multiverse, is one of the most fascinating topics in science. It suggests there could be other universes beyond our own, each with its own set of rules, events, and possibilities. This concept challenges how we see the world and our place in it. To understand why scientists even consider the possibility of parallel universes, we need to take a closer look at what led to these ideas. Our universe follows laws of physics that we've spent centuries trying to understand. These laws, like gravity and electromagnetism, explain how planets move, how stars shine, and even how particles interact at the smallest scales. Yet, as much as we know, there are things we can't explain fully. For example, why did our universe take the shape it has today? Why are the constants in physics, like the speed of light or the strength of gravity, set at exactly the values they are? If they were even slightly different, stars might not form, planets might not exist, and life as we know it would never have arisen. This has led scientists to ask, did it have to be this way, or could there be other universes where the rules are different? One of the main ideas supporting the possibility of parallel universes comes from a theory called cosmic inflation. This theory says that in the very first moments after the Big Bang, the universe expanded incredibly quickly. It grew faster than the speed of light, stretching space itself. This rapid expansion is why the universe appears smooth and uniform on large scales, but it also hints at something deeper. If inflation happened in our universe, it could have happened in other regions of space too. These other regions might have formed their own universes, each separate from ours. They might have different laws of physics, different kinds of particles, or entirely different dimensions. Another reason scientists think about parallel universes comes from quantum mechanics. This branch of science deals with the behavior of particles at the smallest scales, like electrons and photons. In the quantum world, particles don't follow fixed paths. Instead, they exist in a mix of possibilities until something measures or observes them. This is called superposition. For example, imagine flipping a coin. In our everyday world, it lands heads or tails. But in the quantum world, it's as if the coin is both heads and tails at the same time until you look at it. Some interpretations of quantum mechanics suggest that every time a particle makes a choice, the universe splits. In one version, the particle goes one way. In another version, it goes a different way. If this is true, there could be countless versions of reality, each representing a different outcome of every possible event. To make this idea easier to picture, imagine you're at a crossroads. You can choose to turn left or right. In one universe, you choose left. In another, you choose right. Each choice creates a new universe, where events unfold differently from that point on. Over time, these universes would grow more and more different from one another. Some might still resemble the world you know, while others might be completely unrecognizable. This concept is often called the many worlds interpretation of quantum mechanics. While these ideas sound exciting, they're hard to prove. One major challenge is that if other universes exist, they're likely beyond our ability to observe. Our tools like telescopes and particle accelerators are built to study this universe. Even if another universe were right next to ours, it might be completely cut off from us. Think of two bubbles floating side by side. They might touch briefly, but what happens inside one bubble doesn't affect the other. If universes are like bubbles, we might never find a way to look into another one. Still, scientists are looking for clues. One place they're searching is in the cosmic microwave background, which is a faint glow left over from the Big Bang. This light has tiny variations that tell us about the early universe. Some researchers have wondered if unusual patterns in this light could be evidence of another universe bumping into ours. So far, no conclusive evidence has been found, but the search continues. Another way scientists explore the multiverse idea is through mathematics. Many theories in physics predict the existence of parallel universes, even if they don't directly prove it. For example, string theory, which tries to explain how everything in the universe works, suggests there could be extra dimensions of space that we can't see. These extra dimensions might give rise to other universes, each with its own unique structure. While these ideas are still theoretical, they show how the concept of parallel universes fits into broader attempts to understand reality. It's important to recognize that these ideas, as intriguing as they are, remain unproven. Some scientists argue that if parallel universes can't be observed, they don't belong in science. They see the multiverse as more of a philosophical question than a scientific one. Others disagree, pointing out that many scientific discoveries started as untestable ideas. For example, the existence of atoms was debated for centuries before experiments finally confirmed them. By exploring the multiverse, we might uncover new ways to test these ideas and expand our understanding of the universe. If parallel universes do exist, they raise profound questions. Are there versions of ourselves living different lives in these other worlds? Could we ever communicate with them? And what would it mean for our understanding of existence? These questions go beyond physics, touching on philosophy, ethics, and even our sense of identity. They remind us how much we still don't know and how much there is to discover. For now, the idea of parallel universes remains a topic of exploration and debate. It challenges us to think beyond the boundaries of what we can see and measure. Whether or not we ever find proof, the search itself pushes the limits of science and imagination. In trying to understand the multiverse, we are also trying to understand the nature of reality and our place within it. That journey, even without clear answers, is a testament to human curiosity and the drive to explore the unknown. Human memory is a remarkable system that allows us to retain, recall, and use information. It shapes our identity and helps us navigate the world. Memory is not a single thing, but a collection of processes that work together. To understand how it works, it helps to think about it as having three main parts: encoding, storage, and retrieval. Encoding is the first step in forming a memory. It happens when information from the world around us enters our brain. Imagine you meet a new person at a party. You hear their name, notice their face, and perhaps even shake their hand. Your senses, sight, hearing, touch, take in this information and send it to your brain. Your brain organizes this information, deciding what to keep and what to let go. It's a bit like taking notes during a lecture. If something grabs your attention or feels important, you're more likely to remember it later. For example, if the person you meet shares the same name as your best friend, you might make a mental connection that helps you remember. Storage is the next step. Once information is encoded, it has to be stored so you can access it later. The brain uses different types of memory storage, depending on how long you need the information. Sensory memory holds on to information for just a moment. It's like a flash of lightning. It appears and disappears quickly. For example, when you see a car drive past, you might remember its color for a second or two, but then it fades. Short-term memory, or working memory, holds information for a bit longer, usually around 15 to 30 seconds. It's like writing something on a chalkboard. You can keep it there as long as you're focused on it, but if you stop paying attention, it gets erased. Long-term memory is for information you want to keep longer, sometimes for a lifetime. It's like saving a file on a computer hard drive. This storage can hold a vast amount of information, from childhood memories to facts you learn in school. Retrieval is the final step in memory. It's the process of accessing stored information when you need it. This happens when you try to remember something, like the name of the person you met at the party. Sometimes retrieval is easy, like when you instantly recognize your favorite song on the radio. Other times, it can be tricky. You might feel like the information is on the tip of your tongue, but just out of reach. This happens because memory retrieval depends on many factors, including how the information was encoded and whether there are cues to trigger it. For instance, hearing a song that was playing at the party might remind you of the person you met. To understand memory better, it helps to know that it is not a perfect system. Memory is not like a camera that captures an exact copy of what happened. Instead, it's more like a storyteller. The brain takes bits of information and pieces them together to create a memory. This means that memories can change over time. For example, if you tell a story about a childhood event again and again, you might add or change details without realizing it. This is why eyewitness testimony in court cases can sometimes be unreliable. Scientists have identified different types of memory that serve specific purposes. Episodic memory is one type. It helps you remember events from your life, like your last birthday or your first day of school. Semantic memory is another type. It stores general knowledge, like the fact that the capital of France is Paris. Procedural memory is different because it helps you remember how to do things, like riding a bike or tying your shoes. These types of memory are stored in different parts of the brain, and they work together to help you navigate daily life. The brain uses specific areas to process and store memories. The hippocampus is especially important for forming new memories. If you think of the brain as a library, the hippocampus acts like the librarian, helping to organize and file information. Damage to the hippocampus can make it hard to form new memories, even though older ones might remain intact. Other parts of the brain, like the amygdala, play a role too. The amygdala is involved in emotional memories. That's why you might remember a scary experience vividly, even if it happened years ago. Forgetting is a natural part of how memory works. It might seem frustrating, but forgetting can actually be helpful. If you remembered every single thing you ever experienced, it would be overwhelming. Forgetting allows your brain to clear out information that's no longer useful, making room for what's important. There are several reasons why we forget. Sometimes it's because the information wasn't stored properly in the first place. Other times, memories fade because we haven't used them in a long time. This is like a path in the woods that gets overgrown if no one walks on it. Forgetting can also happen when old memories interfere with new ones, or when new information makes it harder to recall older memories. Age can affect how memory works. As people get older, they might find it harder to remember names or where they put their keys. This is a normal part of aging, but it can also be a sign of more serious conditions, like Alzheimer's disease. In Alzheimer's, the brain's ability to store and retrieve memories becomes damaged. This is why scientists are studying memory so closely, hoping to find ways to protect and improve it. Memory can also be affected by stress, sleep, and lifestyle. Stress can make it harder to focus and remember things, while sleep plays a key role in consolidating memories. During sleep, the brain strengthens the connections that help you retain what you learned during the day. This is why a good night's sleep is important before a big exam. Healthy habits, like regular exercise and a balanced diet, also support memory by keeping the brain in good condition. One of the most fascinating aspects of memory is its flexibility. While this means memories can be altered or forgotten, it also means they can be improved. Techniques like repetition and association can help you remember better. For example, if you're trying to learn a new language, practicing the words regularly and linking them to familiar concepts can make them stick. Visualization is another tool. If you're trying to remember a list of items like groceries, you might picture each one in your mind. Creating strong connections during encoding makes retrieval easier later. Human memory is a complex system that blends biology, psychology, and experience. It allows us to learn, adapt, and connect with others. While it isn't perfect, it's incredibly powerful. By understanding how it works, we can find ways to make the most of it, improving not just how we remember, but how we live. Cultural evolution refers to the way human culture changes over time. It happens as people adopt new ideas, behaviors, and technologies, then pass them to others. This process shapes everything from the way societies organize themselves to the languages we speak and the tools we use. Cultural evolution isn't random. It follows patterns, and those patterns are shaped by a variety of factors, including human creativity, environmental challenges, and social interactions. Understanding what drives these changes can help explain why cultures develop differently and how they adapt to changing circumstances. At its core, cultural evolution depends on transmission. Humans have the unique ability to share knowledge and behaviors. This happens through communication, imitation, and teaching. When someone invents a better way to hunt, builds a stronger shelter, or develops a new way of farming, that knowledge spreads. Over time, people modify and improve on it, creating a cycle of innovation and refinement. This ability to share and build on ideas sets humans apart from other species. While some animals like chimpanzees and dolphins pass on behaviors, their cultural transmission is limited compared to humans. One driving force behind cultural evolution is survival. When people face challenges, they come up with solutions that help them adapt. For example, early humans living in colder climates developed clothing and fire to stay warm. In hot, dry regions, they figured out how to store water and build shelters that stayed cool. These adaptations often became traditions, passed from one generation to the next. Over time, small changes to these practices made them even more effective. Survival challenges often push people to think creatively and come up with new ideas, which then spread through the group. Another factor influencing cultural evolution is the environment. Natural resources, climate, and geography shape how people live. A society near a river might develop fishing techniques and trade routes based on water travel. In contrast, a desert community might focus on irrigation and conserving resources. These environmental pressures often lead to distinct cultural practices. Even today, we see this influence. Urban cultures, for instance, tend to develop faster-paced lifestyles and innovative solutions to crowded living conditions, while rural communities often maintain traditions tied to farming and the land. Social interaction also plays a major role. Humans are social creatures, and much of our culture develops through relationships. When people interact, they exchange ideas, stories, and behaviors. This exchange creates a shared understanding, which forms the basis of culture. As groups grow larger and more connected, cultural evolution speeds up. Trade, migration, and technology, such as the internet, have made it easier than ever for ideas to spread. For example, foods that were once limited to specific regions, like sushi or tacos, are now enjoyed worldwide because of cultural exchange. Technology has always been a significant driver of cultural change. The invention of tools, writing, and machines changed the way people lived and worked. Each major technological breakthrough opened up new possibilities. Writing, for example, allowed people to record their knowledge and pass it on to future generations. This made it possible to build on past achievements, leading to faster progress. Similarly, the printing press spread ideas to a wider audience, and the internet has created a global network for sharing information almost instantly. Technology not only solves problems, but also reshapes how people interact with one another in the world. Cultural evolution is not always a smooth process. Sometimes new ideas or technologies disrupt traditional ways of life. This can lead to conflict between those who embrace change and those who resist it. For example, when industrial machines replaced manual labor in the 19th century, many workers lost their jobs, leading to unrest. In other cases, cultural evolution brings unintended consequences. The rise of social media, for instance, has connected people in ways that were unimaginable a few decades ago. But it has also led to concerns about misinformation and its impact on mental health. One unique aspect of cultural evolution is that it doesn't follow the same rules as biological evolution. While biological traits are passed down genetically, cultural traits spread through learning and imitation. This means cultural evolution happens much faster. A good example is language. A new word or phrase can become popular within weeks, especially in the age of social media. This speed allows cultures to adapt quickly to new challenges, but it also means that cultural trends can change just as fast. One interesting example of cultural evolution in action is the development of democracy. In ancient times, most societies were ruled by kings or emperors. Over centuries, ideas about fairness and shared power began to take hold. Philosophers like Plato and Aristotle debated the merits of different forms of government. These ideas influenced societies over time, leading to experiments with representative government in places like Athens. Today, democracy has spread around the world, adapting to fit the needs and values of different cultures. Cultural evolution is also shaped by values and beliefs. What a society considers important influences how it changes. For example, a culture that values education will invest in schools and encourage learning, which can lead to technological and artistic advancements. On the other hand, a culture that prioritizes tradition may work to preserve its heritage, focusing on continuity rather than change. Values guide the direction of cultural evolution, often balancing innovation with the need to maintain a sense of identity. The spread of ideas, often called diffusion, is another driver of cultural evolution. When two cultures come into contact, they influence each other. This has happened throughout history, from the Silk Road trade routes to modern globalization. The result is often a blending of traditions, like how jazz music combines African rhythms with European instruments. Diffusion creates new opportunities for innovation, but it can also create tension as cultures struggle to balance old and new influences. Cultural evolution continues to shape the world we live in. Advances in technology, global communication, and environmental challenges are driving rapid changes. At the same time, people are looking for ways to preserve their cultural heritage in the face of globalization. This balance between change and tradition is a central theme in cultural evolution. It reminds us that while cultures may evolve in response to new challenges, they are also deeply rooted in the values and knowledge of the past. Ultimately, what drives cultural evolution is the human ability to learn, adapt, and share. It is a process that reflects both our creativity and our need to connect with one another. As long as humans face challenges and interact with each other, cultural evolution will continue to shape our world, offering both opportunities and challenges as we move forward. By understanding the factors that drive this process, we can better navigate the changes and ensure that cultural evolution works for the benefit of all. Magnetic fields are fascinating features of planets and stars, shaping the environments around them in powerful ways. They protect planets like Earth from harmful solar radiation and create the dazzling auroras at the poles. They also guide charged particles in space and influence the behavior of plasma in stars. But understanding where these magnetic fields come from involves looking deep inside these objects to study the motion of materials and how they interact. Magnetic fields are created by moving electric charges. This idea is based on a principle from physics called electromagnetism. In planets and stars, these electric charges are carried by conducting materials, like molten metal or charged gas, moving in specific ways. To understand how this works, imagine stirring a pot of soup. If the soup is just sitting still, nothing much happens. But when you start stirring it, the motion creates swirls and patterns in the liquid. In planets and stars, these swirls happen in materials that can carry electrical currents, and this movement can generate magnetic fields. In planets like Earth, the magnetic field comes from a process called the dynamo effect. The Earth has a core made of iron and nickel, with the outer part of the core being liquid metal. This liquid metal moves because of heat coming from the inner core and the rotation of the planet. The heat causes convection, a process where hotter material rises and cooler material sinks, creating a churning motion. The rotation adds another layer of complexity, causing the moving liquid to form spiral patterns. These patterns create electric currents, and those currents generate the magnetic field. The Earth's magnetic field isn't static. It changes over time as the motions in the core evolve. Sometimes the field even flips, with the magnetic north and south poles switching places. These reversals have happened many times in Earth's history, although they occur over thousands of years, so they don't disrupt life in a sudden way. Scientists study these changes by examining rocks that recorded the direction of the magnetic field when they formed. This helps us understand the long-term behavior of the magnetic field and the processes in the Earth's core. Other planets in our solar system have magnetic fields too, but they vary widely. Jupiter, for example, has a magnetic field that is much stronger than Earth's. This is because Jupiter's core is surrounded by a layer of metallic hydrogen, a form of hydrogen that acts like a metal under extreme pressure. The rapid rotation of Jupiter adds to the dynamo effect, creating a strong and extensive magnetic field. On the other hand, Mars has a very weak magnetic field. Scientists believe this is because Mars no longer has a liquid outer core, so the dynamo effect has stopped. The loss of its magnetic field left Mars vulnerable to solar wind, which stripped away much of its atmosphere over time. In stars, magnetic fields are created in a similar way but involve different materials and much larger scales. Stars like the Sun are made mostly of plasma, a state of matter where electrons are free to move around rather than being bound to atoms. This plasma is an excellent conductor of electricity. The Sun's magnetic field comes from the motion of this plasma in its interior. The Sun has layers, and the motion of plasma in these layers, combined with the Sun's rotation, generates electric currents. These currents produce the Sun's magnetic field. The Sun's magnetic field is not simple or uniform. It changes over an 11-year cycle, during which the Sun's magnetic poles switch places, just like Earth's field does, but on a much shorter timescale. This cycle also affects solar activity, like the number of sunspots and solar flares. Sunspots are areas where the magnetic field is particularly strong, and solar flares are bursts of energy caused by changes in the magnetic field. These events can have effects on Earth, such as disrupting satellites and power grids. Stars more massive than the Sun also have magnetic fields, and these can be even more complex. Their rapid rotation and turbulent interiors can create powerful magnetic fields that influence their behavior. For example, magnetic fields can affect how stars lose mass over time and how they interact with nearby stars or planets. In some cases, when massive stars die in supernova explosions, their magnetic fields can intensify, leading to the creation of magnetars. Magnetars are a type of neutron star with magnetic fields so strong they can affect atoms and molecules in extreme ways, breaking them apart. The processes that create magnetic fields in planets and stars are complex, but scientists study them using a combination of observations, experiments, and computer simulations. For example, researchers study Earth's magnetic field using satellites and ground-based measurements. They also create models of the Earth's core in laboratories to see how liquid metals behave under similar conditions. For stars, telescopes that detect light across different wavelengths help scientists observe magnetic activity, like sunspots and flares. Advanced simulations use supercomputers to model the motion of plasma and predict how magnetic fields develop and evolve. Understanding the origin of magnetic fields is not just about curiosity. These fields play a key role in shaping the environments of planets and stars. On Earth, the magnetic field protects life by deflecting harmful solar and cosmic radiation. Without it, the atmosphere might be stripped away, as happened on Mars. For space exploration, knowing how magnetic fields work helps scientists design spacecraft and satellites that can withstand the effects of space weather, such as solar flares. On a larger scale, understanding magnetic fields in stars helps us learn about the life cycles of stars and how they influence the formation of planets and the conditions for life elsewhere in the universe. Magnetic fields also connect to many other areas of physics and astronomy. They are tied to questions about the origins of planets and stars, the behavior of plasma in extreme conditions, and even the large-scale structure of galaxies. By studying magnetic fields, scientists can gain insights into these broader topics and deepen our understanding of the universe. While we have made significant progress in understanding how magnetic fields originate in planets and stars, many questions remain. For instance, the exact details of how turbulence in a planet's core or a star's plasma leads to the generation of magnetic fields are still being studied. The relationship between magnetic fields and the rotation of a planet or star is also an area of active research. As scientists continue to explore these mysteries, they will uncover new details about the forces shaping our world and the universe around us. The question of how long humans can live has intrigued scientists, philosophers, and societies for centuries. People have always been fascinated by the idea of extending life, pushing the boundaries of what the human body can endure. To understand the limits of human longevity, it helps to look at the combination of biology, environment, and technology that shapes our lives. While we've made remarkable progress in extending life expectancy over the past century, the maximum lifespan of humans still appears to have a ceiling. The first thing to consider is how the human body ages. Our bodies are made up of cells that grow, divide, and eventually wear out. Over time, this process leads to a gradual decline in how well our organs and systems function. The mechanisms that drive aging are not completely understood, but scientists know that damage accumulates in our DNA, proteins, and cells. For example, every time a cell divides, it copies its DNA, but these copies aren't perfect. Mistakes in replication build up and can lead to dysfunction. Cells also have telomeres, which are like protective caps on the ends of DNA strands. With each division, these telomeres shorten. Eventually, they become too short for the cell to divide, leading to cellular aging and death. At the same time, other processes like oxidative stress and inflammation contribute to aging. Oxidative stress occurs when molecules in the body, called free radicals, damage cells and tissues. Inflammation is the immune system's response to damage, but chronic inflammation can harm tissues instead of protecting them. These processes wear down our bodies over time, limiting how long they can function properly. The idea that there might be a natural limit to human longevity has gained attention from researchers. Studies of the oldest people in the world, often called supercentenarians, suggest that even under the best conditions, human lifespans rarely exceed 120 years. For example, Jane Calment, a French woman, holds the record for the longest confirmed human lifespan at 122 years. She lived in a time before modern medical advances like organ transplants or advanced cancer treatments, suggesting that natural biological factors were crucial in her extraordinary longevity. However, even in her case, the body eventually reached its limit. Some scientists argue that human longevity is determined by a combination of genetics and environmental factors. Genetics play a significant role in how well our cells repair themselves and resist damage. For example, some people inherit genes that help protect against diseases like heart disease or Alzheimer's, which can extend life. Studies of families with long-lived members have shown that longevity often runs in families, suggesting a strong genetic component. However, environment and lifestyle are just as important. Advances in healthcare, better hygiene, and access to nutritious food have contributed to longer lives for many people. In the early 1900s, life expectancy was much lower than it is today, often below 50 years in many parts of the world. Improvements in medicine, such as vaccines and antibiotics, drastically reduced deaths from infectious diseases. Public health measures like clean water and better sanitation also played a major role. Today, people live longer because they are less likely to die from preventable diseases or accidents early in life. Even though modern medicine has extended life expectancy, there are limits to what it can do to stop the aging process. Organ systems, like the heart and lungs, have natural limits on how long they can function. The heart, for example, beats around 100,000 times a day, which adds up to more than 3 billion beats over an average lifetime. Over time, the heart's ability to repair itself declines. Similarly, the brain experiences changes as neurons die and connections weaken, which can lead to conditions like dementia. Some researchers believe that we could extend human longevity by targeting the biological mechanisms of aging directly. This is an area of intense study, often called geroscience. Scientists are exploring ways to slow or even reverse aging at the cellular level. For example, experiments on animals have shown that certain drugs, like rapamycin, can extend lifespan by affecting how cells grow and repair themselves. Other studies focus on reactivating telomerase, an enzyme that rebuilds telomeres and could theoretically extend the life of cells. While these studies are promising, they also face significant challenges. The human body is incredibly complex, and tinkering with one system often has unintended consequences. For example, reactivating telomerase might allow cells to live longer, but it could also increase the risk of cancer, as cancer cells rely on telomerase to grow uncontrollably. Similarly, drugs that slow aging in animals might not have the same effects in humans, whose bodies are larger and more complicated. Another important factor is the societal impact of extending human lifespans. If people lived much longer, it could put a strain on resources like healthcare, housing, and food. Pension systems and retirement plans would need to be rethought, and longer lives could also create challenges for younger generations, such as fewer job openings or slower career progression. These are important considerations as scientists work on extending human life. Technology could also play a role in pushing the limits of longevity. Advances in artificial intelligence and robotics might one day allow us to replace damaged organs with synthetic ones, or even upload our consciousness into machines. While these ideas sound like science fiction, researchers are already working on technologies like artificial hearts and neural interfaces. If these innovations become practical, they could change how we think about aging and lifespan. Despite these possibilities, the question remains: is there a maximum lifespan for humans? Some scientists believe that we might eventually break the 120-year barrier, but others argue that the fundamental processes of aging are too ingrained in our biology to overcome completely. Even if we could repair damage to cells and tissues, other factors like environmental exposure and random mutations might still limit how long we can live. For now, the best way to increase your chances of living a long and healthy life is to focus on what we already know works. Eating a balanced diet, staying physically active, avoiding smoking, and managing stress are proven ways to improve health and extend life. These lifestyle choices might not make you live to 150, but they can help you make the most of the years you have. The limits of human longevity are both a biological question and a societal one. While researchers continue to explore ways to extend life, they are also uncovering the trade-offs and challenges that come with it. Whether we can overcome these limits remains an open question. but understanding the science of aging brings us closer to finding the answers. Mass extinctions are events when large numbers of species disappear in a relatively short time. These events leave a lasting mark on the planet, reshaping ecosystems and altering the course of evolution. To understand what triggers these catastrophes, it helps to look at both natural forces and the delicate balance that sustains life. Over Earth's history, scientists have identified 5 major mass extinctions, each caused by different factors, but all share a common thread: a sudden and overwhelming disruption of environmental stability. One of the most well-known examples of a mass extinction is the event that wiped out the dinosaurs about 66 million years ago. This extinction, often linked to an asteroid impact, provides a good starting point. Imagine a rock the size of a small city hurtling through space, striking Earth with unimaginable force. When it hit, it released energy equivalent to billions of nuclear bombs, creating a massive crater and sending debris into the atmosphere. This debris blocked sunlight for months, plunging the planet into darkness and disrupting photosynthesis. Plants couldn't grow, animals that depended on them starved, and entire food chains collapsed. This one event caused the extinction of about 75% of all species at the time. Asteroid impacts, while dramatic, aren't the only cause of mass extinctions. Volcanic eruptions have also played a major role. For example, around 252 million years ago, during what's known as the Permian-Triassic extinction, volcanic activity in what is now Siberia released vast amounts of gases like carbon dioxide and methane into the atmosphere. These gases caused global temperatures to rise. As the oceans warmed, they lost their ability to hold oxygen, creating dead zones where life could no longer survive. Many marine species which rely on oxygen in the water perished. On land, the rising heat and changing climate made survival difficult for countless other organisms. This event, sometimes called the Great Dying, wiped out about 96% of marine species and 70% of land species. Climate change, whether caused by volcanic activity or other factors, often plays a role in mass extinctions. Life depends on stable temperatures and predictable weather patterns. When these change too quickly, many species can't adapt in time. For instance, during the late Ordovician extinction, about 443 million years ago, the planet went through a period of global cooling. Ice sheets expanded, sea levels dropped, and shallow marine habitats disappeared. Many species that lived in these habitats, such as certain types of trilobites and brachiopods, went extinct because they couldn't survive in the new conditions. Another major factor in mass extinctions is the level of oxygen in the atmosphere and oceans. Life as we know it depends on oxygen, but this hasn't always been abundant on Earth. About 2.4 billion years ago, during the Great Oxidation event, oxygen levels in the atmosphere rose dramatically. While this paved the way for more complex life forms, it also wiped out many species that had evolved to live in low oxygen environments. Conversely, when oxygen levels drop, as they did during several extinction events, many species that rely on it struggle to survive. For example, during the Devonian extinction about 375 million years ago, changes in ocean chemistry likely led to lower oxygen levels, contributing to the loss of many marine species. Mass extinctions can also result from disruptions caused by external forces, like changes in Earth's orbit or solar activity. These changes can alter the amount of energy the planet receives from the sun, leading to shifts in climate. While these processes are slow, they can set off a chain reaction of events that destabilize ecosystems. For example, during the End-Triassic extinction about 201 million years ago, it's believed that a combination of volcanic activity and changes in the carbon cycle led to rapid warming and ocean acidification. These conditions made it nearly impossible for coral reefs and other marine organisms to survive, leading to a cascade of extinctions. Diseases and biological factors can also contribute to mass extinctions. In some cases, invasive species or new pathogens can spread quickly, disrupting ecosystems and outcompeting or killing native species. While these biological triggers are more localized, they can amplify the effects of other environmental changes, leading to a broader collapse of biodiversity. For example, during the late Devonian extinction, it's possible that certain plant species which began to colonize land changed the soil and released nutrients into rivers and oceans. This may have caused algae blooms that consumed oxygen in the water, creating dead zones where marine life couldn't survive. It's worth noting that mass extinctions don't always happen overnight. While some, like the asteroid impact that ended the age of dinosaurs, occur suddenly, others unfold over thousands or even millions of years. This slow pace doesn't make them any less devastating. In fact, gradual events can be harder for species to recover from because they disrupt ecosystems for such a long time. Today, some scientists argue that we are living through a sixth mass extinction, one caused not by asteroids or volcanic eruptions, but by human activity. Habitat destruction, pollution, overhunting, and climate change are all contributing to a rapid loss of biodiversity. For example, the clearing of rainforests for agriculture destroys habitats for countless species, while rising global temperatures threaten coral reefs and the marine life that depends on them. Unlike past extinctions, which were caused by natural events, this one is driven by human actions, making it unique in Earth's history. Understanding what triggers mass extinctions helps scientists predict and possibly prevent future biodiversity crises. By studying the past, they've learned that life is resilient, but it also has limits. When the environment changes too much or too quickly, species can't adapt, and ecosystems collapse. This knowledge is a reminder of the delicate balance that sustains life on Earth and the importance of preserving it. Each mass extinction teaches us something about the planet and the forces that shape it. They show how interconnected life is, how a change in one part of the system can ripple through the rest. They also highlight how fragile ecosystems can be, especially in the face of rapid change. Whether caused by asteroids, volcanic eruptions, climate shifts, or human activity, quantum measurement is one of the most puzzling concepts in physics. It deals with how the act of observing or measuring something in a quantum system seems to change what we observe. At its core, it raises a question. Why does the act of looking at a quantum object affect its state? To understand this, let's start with how quantum systems behave and why measurement plays such a crucial role. Imagine you're trying to observe a very small particle, like an electron. Electrons, like all quantum objects, don't behave like things we encounter in our everyday lives. Instead of existing in a specific place, they exist in a cloud of probabilities. This cloud represents all the possible places the electron could be. For example, an electron around an atom doesn't sit still like a marble on a table. Instead, it has a range of places it's likely to be, which we can calculate with something called a wave function. The wave function gives us the probability of finding the electron in any particular spot if we look for it. But here's the strange part. The electron doesn't seem to have a definite position until we measure it. When we do, the act of measurement forces the electron to choose one location out of all the possibilities. Before we measure, the electron isn't in one specific place. It's in a superposition of many possible states. This is not something we see in the macroscopic world, where objects like chairs and cars have fixed positions whether or not we're looking at them. Let's use an example to make this clearer. Imagine you're blindfolded and throwing a ball at a dartboard. You know the dartboard is there, and you have some idea of where the ball might land. But until you take off the blindfold and look, you don't know the exact spot. Quantum systems are like that dartboard, except the ball is everywhere on the board at once until you observe it. When you finally take off the blindfold, the ball appears in one specific spot. That's what happens when you measure a quantum system. The act of looking fixes the result. This process of fixing a result is called wave function collapse. Before measurement, the wave function describes all possible outcomes. After measurement, it collapses into a single outcome, the one you observe. But why does this happen? That's the mystery. Physicists don't fully understand why measurement has this effect. The equations of quantum mechanics, like the Schrödinger equation, describe how the wave function evolves over time. However, they don't explain why observing or measuring a system causes it to collapse. One of the most famous thought experiments to illustrate this mystery is Schrödinger's cat. In this scenario, a cat is placed inside a box with a vial of poison, a radioactive atom, and a mechanism that breaks the vial if the atom decays. The atom's decay is a quantum event. It can either decay or not decay, and before we observe it, it's in a superposition of both states. This means the cat is both alive and dead at the same time, at least until someone opens the box and observes the system. Once you open the box, the superposition collapses and the cat is either alive or dead. This thought experiment shows how quantum measurement can produce bizarre results when applied to larger systems. But what does it mean to measure something? In quantum mechanics, measurement isn't just about looking with your eyes or using a device to record data. It involves any interaction that causes a quantum system to interact with its environment in a way that leaves a record. For example, if an electron interacts with a photon of light, that interaction can count as a measurement. The key point is that the interaction forces the quantum system into one of its possible states, collapsing the wave function. One interpretation of quantum mechanics, called the Copenhagen interpretation, says the collapse happens because we interact with the system. This interaction makes the system choose one outcome, and that's what we see. Another interpretation, called the many worlds theory, takes a different approach. It says that the wave function never collapses. Instead, when we measure a quantum system, the universe splits into multiple branches. In one branch, the electron is in one position, and in another branch, it's somewhere else. Both outcomes happen, but we only experience one. To make things even more puzzling, experiments have shown that the timing of measurement can affect the outcome. For example, in a famous experiment called the double-slit experiment, particles like electrons or photons are sent toward a barrier with two slits. If no one measures which slit the particle goes through, it behaves like a wave and creates an interference pattern on a screen behind the barrier. This pattern shows that the particle acted like it went through both slits at once. But if you measure which slit the particle goes through, the interference pattern disappears, and the particle behaves like it only went through one slit. This experiment shows how the act of measurement determines whether the particle behaves like a wave or a particle. Some physicists have tried to explain quantum measurement using concepts like decoherence. Decoherence happens when a quantum system interacts with its environment, causing the superposition to break down into classical states. For example, if an electron interacts with a bunch of other particles, those interactions effectively measure the electron and force it into one specific state. While decoherence explains how quantum systems lose their superpositions, it doesn't fully explain why measurement causes the collapse. Others have explored whether consciousness plays a role in quantum measurement. Some interpretations suggest that the observer's mind is what causes the wave function to collapse. This idea is controversial and not widely accepted in the scientific community, but it shows how deeply the concept of measurement challenges our understanding of reality. At the heart of this mystery is a fundamental question. Does the universe exist in a definite state when no one is looking, or does it only take on definite states when observed? Quantum mechanics doesn't provide a clear answer. It gives us powerful tools to predict probabilities and describe systems mathematically, but it doesn't explain why the act of measurement works the way it does. To understand how strange this is, imagine flipping a coin. In the classical world, the coin lands either heads or tails, whether or not you look at it. In the quantum world, the coin is in a superposition of heads and tails until you check. That simple act of checking changes the outcome, and we don't fully understand why. Physicists continue to debate the nature of quantum measurement and how it fits into our understanding of the universe. Some believe we need a new theory that goes beyond quantum mechanics to explain it. Others think the mystery lies in the way we interpret the equations of quantum mechanics. Whatever the answer, it's clear that quantum measurement touches on some of the deepest questions about the nature of reality and our place in it. Understanding it fully may require us to rethink how we see the world, much as quantum mechanics itself forced us to do over a century ago.